Please subscribe to support the channel. Have you ever wondered if there could be a star, far away in the depths of our galaxy, that might one day unleash a force so powerful it could potentially threaten life on Earth, even from thousands of light years away? It sounds like the plot of a science fiction movie, doesn't it? But this isn't fiction. Astronomers have long studied a star known as WR-104, often referred to as the Pinwheel Star, and it's one of the most mysterious and fascinating objects in the universe. The very thought that something so distant could still pose a potential risk sparks both awe and a touch of unease. But it also opens up a world of discovery, because WR-104 is more than just a cosmic threat. It's a window into the life and death of the most massive stars in our galaxy. When we look up at the night sky, most of the stars we see are ordinary, stable, long-lived stars like our Sun. But WR-104 is anything but ordinary. It belongs to a rare and extreme category of stars that live fast, burn furiously bright, and die young. These stars are volatile, shedding their outer layers at tremendous speeds and creating spectacular cosmic structures. WR-104 in particular has captured scientific attention because of its unique appearance, its possible fate, and the slim, but not impossible, chance that its death throes could one day affect our planet. So as we dive into the story of this enigmatic star, keep this in mind. WR-104 is a reminder of how small we are compared to the colossal forces at play in the universe. Its story is one of beauty and danger, of cosmic artistry and raw destructive power. And while the risks it poses to us are vanishingly small, the fascination it inspires is immeasurable. With that, let's start unraveling the mysteries of WR-104, beginning with what it actually is and why astronomers are so captivated by it. The star we're focusing on carries the scientific designation WR-104, but most people know it by a far more captivating nickname, the Pinwheel Star. Just hearing that name paints a vivid picture of something whimsical, colorful, and spinning gracefully in space. But in reality, this object is far more complex, far more massive, and far more dangerous than the toy its nickname suggests. To truly appreciate what makes the Pinwheel Star so special, we first need to pin down its identity in astronomical terms. WR-104 belongs to a rare class of stars known as Wolf-Rayet stars. These are among the hottest, most luminous, and most short-lived stars in the galaxy. Unlike ordinary stars like our Sun, which can quietly burn hydrogen for billions of years, a Wolf-Rayet star is a ticking time bomb. It represents one of the final stages in the life cycle of a very massive star, a stage that comes just before the inevitable collapse and explosive death known as a supernova. And in some cases, like the Pinwheel Star, there's the possibility of an even more powerful finale, a gamma-ray burst. But let's locate it first. The Pinwheel Star resides in the constellation Sagittarius, a part of the sky many people recognize as the home of the center of our Milky Way galaxy. It's nestled about 8,000 light-years away from us, a staggering distance when measured in human terms, but relatively close when we consider the scale of the galaxy. To put it in perspective, light traveling at nearly 300,000 kilometers per second still takes 8,000 years to reach us from the Pinwheel Star. That means when we observe it with our telescopes today, we're not seeing it as it is right now. We're seeing it as it was during the time of ancient human civilizations, back when people on Earth were just beginning to form written languages. The Pinwheel Star is essentially a time capsule, showing us a cosmic event frozen thousands of years in the past. Its official name, WR-104, comes from the Wolf-Rayet catalog, which classifies these rare stars by their spectral signatures. The WR indicates that it's a Wolf-Rayet star, and the number 104 simply means it was the 104th entry in that particular catalog. But of course, numbers and catalog labels don't quite capture the poetic nature of this object. That's why the nickname Pinwheel Star stuck so firmly, because its appearance is unlike anything else we've seen in the cosmos. Through high-resolution imaging, astronomers have observed an extraordinary spiral of dust and gas unwinding from the star, shaped by the gravitational and energetic forces of a nearby stellar companion. From our perspective on Earth, this structure resembles a glowing, spiraling pinwheel frozen against the blackness of space. Understanding what the Pinwheel Star is also means understanding what it is not. This isn't just a single, solitary star hanging in the void. WR-104 is part of a binary system, meaning it shares its stellar neighborhood with another massive star. The interplay between these two stars is key to its identity and to the spectacular spiral that has made it famous. But before we dive into that detail in later segments, let's stay grounded in the basics. WR104 is a Wolf-Rayet star, extremely hot, extremely luminous, and on the cusp of its explosive demise. To further highlight just how exotic it is, consider this. If the Pinwheel Star was swapped with our Sun and placed at the center of our solar system, life on Earth wouldn't just be disrupted, it would be impossible. Its intense radiation, its powerful stellar winds, and its extreme luminosity would strip away atmospheres, boil oceans, and sterilize everything in seconds. This is a star that radiates tens of thousands of times more energy than our Sun, a cosmic furnace blazing with unimaginable intensity. And yet, from the safety of 8,000 light-years away, we can marvel at its beauty without fear, at least for now. The Pinwheel Star's identity has also made it one of the most studied Wolf-Rayet systems in astronomy. It's often cited in discussions of stellar evolution, supernova mechanics, and gamma-ray burst origins. That's because its orientation and activity provide a rare laboratory to test theories about how the universe's most powerful explosions unfold. While countless Wolf-Rayet stars exist throughout the Milky Way, very few present themselves in such a striking, observable form. The fascination with WR104 also highlights a bigger theme in astronomy: the human tendency to give cosmic objects names that reflect both their appearance and their mystery. Numbers like WR104 serve scientists well, but names like Pinwheel Star capture the imagination of the public. They remind us that behind every cold measurement of distance, mass, and luminosity, there is a story, one that connects us emotionally to the universe. And in this case, the story is that of a star that may one day unleash unfathomable power, but which, in the meantime, enchants us with the elegance of its spiral form. So in short, the Pinwheel Star is a Wolf-Rayet star located in Sagittarius, about 8,000 light-years away, catalogued as WR104, and partnered in a binary system with another massive star. Its combination of immense energy, precarious life stage, and breathtaking dust spiral has earned it a reputation as one of the most mysterious and intriguing stars in the universe. And it's that blend of beauty and danger that makes it so endlessly captivating. When astronomers first pointed powerful telescopes toward WR104 and began studying it in detail, what they saw was nothing short of mesmerizing. Rather than appearing as just another bright point of light in the night sky, WR104 revealed an extraordinary spiral-shaped plume of dust, winding outward from the central star system like the delicate arms of a cosmic whirlpool. This astonishingly symmetrical pattern, glowing faintly in infrared images, is what earned the star its now famous nickname, the Pinwheel Star. At first glance, this spiral structure almost looks artificial, as if it were designed with perfect geometry by some unseen hand. But of course, its origin is entirely natural, born from the violent and beautiful interactions between WR104 and its stellar companion. You see, WR104 is not alone. It exists in a binary system, partnered with a massive blue O-type star. Both of these stars are titans, radiating enormous amounts of energy and blasting streams of particles, called stellar winds, into space at millions of kilometers per hour. Now, if either of these stars were isolated, their winds would simply stream outward in all directions, dispersing evenly into the interstellar medium. But because the Pinwheel Star and its companion are locked in a close orbital dance, their winds don't just expand freely. Instead, they collide head-on in the space between them, compressing and interacting in ways that shape the environment around them. Imagine two powerful garden hoses spraying water into one another. The collision creates a turbulent, spiraling spray. On a vastly larger scale, this is what happens with WR104 and its partner star. As their powerful winds slam together, they create regions of compressed gas that cool down and condense into tiny particles of carbon-rich dust. This dust doesn't simply scatter randomly into space. It's carried outward by the orbital motion of the two stars. Since the stars orbit one another every 8 months or so, the dust streams outward in a continuous spiral, much like the trail of smoke from a rotating sparkler. Over time, this process creates a vast, expanding pinwheel of dust that glows faintly when observed in infrared light, where telescopes can peer through the obscuring effects of interstellar dust and reveal the underlying beauty. This spiral isn't just a rough approximation either. It is astonishingly symmetrical, with each winding arm spaced evenly apart, tracing the rhythm of the star's orbit like clockwork. In some images, it looks almost like a miniature galaxy, except instead of billions of stars, it's just dust and gas illuminated by the fierce energy of the central stars. The structure is so striking that when astronomers first captured detailed images of it in the late 1990s, it stunned the scientific community. It looked like something straight out of an artist's imagination, yet it was a real, physical phenomenon occurring thousands of light-years away. And so the nickname Pinwheel Star became the natural way to describe WR104. The spiral pattern is not only beautiful, it is also unique. While other Wolf-Rayet stars in binary systems do produce dust and sometimes spirals, very few are oriented in such a way that we can see their structure so clearly from Earth. In WR104's case, our vantage point is almost perfectly aligned to view the spiral pattern in its full glory, as though the universe were deliberately giving us a front-row seat to this cosmic dance. What makes the spiral even more fascinating is that it's dynamic. It isn't frozen in time like a still photograph. With each orbit of the two stars, the spiral expands outward, and new layers of dust are added to the arms. In effect, the Pinwheel Star is constantly painting its own masterpiece in space, with each turn of its orbit leaving a fresh mark on the canvas of the cosmos. Over thousands of years, this spiral can stretch out for light-years, dispersing into the surrounding interstellar medium and seeding it with the raw materials that may one day contribute to the birth of new stars and planets. The spiral dust plume is also more than just a pretty sight. It holds valuable scientific information. By studying its shape, spacing, and brightness, astronomers can deduce critical details about the Pinwheel Star's orbit, its stellar winds, and its mass loss rate. This, in turn, helps refine our models of how massive stars evolve and die. The dust itself is a fascinating clue, because Wolf-Rayet stars are notorious for blowing away their outer layers. Seeing how that material condenses into dust and spreads outward helps scientists understand how the elements forged in these stars, carbon, oxygen, and more, are recycled into the galaxy. So, the name Pinwheel Star isn't just a poetic flourish. It reflects one of the most visually stunning and scientifically intriguing aspects of WR104. The star has earned this nickname because it quite literally looks like a glowing pinwheel spinning in the darkness of space, its arms unfurling gracefully yet relentlessly, driven by the unstoppable forces of stellar evolution. It is a portrait of motion, symmetry, and cosmic creativity, a reminder that even in the violent processes of stellar death, there can be breathtaking beauty. And yet, behind this beauty lies a deeper tension. The spiral dust plume, for all its elegance, is a sign of a star in turmoil, a star shedding its outer layers, living on borrowed time, and heading inevitably toward a cataclysmic end. The pinwheel is both an artwork and a countdown clock, slowly unwinding the story of a star that will one day erupt in one of the most violent explosions in the universe. To understand the true nature of the Pinwheel Star, we need to step back and examine the kind of star it is, a Wolf-Rayet star. This stage of stellar evolution is one of the most violent, extreme, and short-lived phases that any star can undergo. When we say WR104 is a Wolf-Rayet star, we're essentially saying that it has already left behind the more stable and predictable parts of its life and is now racing toward its inevitable end in a catastrophic explosion. Wolf-Rayet stars, often abbreviated as WR stars, are the cosmic equivalents of aging titans on their deathbeds, still enormously powerful, still burning with incredible energy, but losing control of their own structure. They're massive, unstable, and undergoing extreme transformations. While our Sun, a modest main sequence star, has a calm and steady surface temperature of about 5,500 degrees Celsius, Wolf-Rayet stars blaze with surface temperatures ranging anywhere from 25,000 degrees Celsius to over 200,000 degrees Celsius. The Pinwheel Star itself sits in the lower range of this spectrum at around 40,000 degrees Celsius, which is still hot enough to strip electrons off atoms and produce intense ultraviolet radiation. But what really defines Wolf-Rayet stars is their stellar winds. These winds are unimaginably fierce outflows of gas and particles streaming away from the star's surface at speeds of up to 3,000 kilometers per second. To put that into perspective, that's about 1% the speed of light. Imagine standing near a hurricane so powerful it could rip atoms apart and hurl them across millions of kilometers in seconds. That's the level of ferocity we're talking about here. And the Pinwheel Star isn't just blowing a gentle breeze, it's shedding enormous amounts of mass through these winds. In fact, a typical Wolf-Rayet star can lose the equivalent of the Sun's entire mass in just a few 100,000 years. Why does this happen? The answer lies in the life history of massive stars. Stars like WR104 start out much larger than our Sun, often 20, 30, or even 50 times as massive. They burn through their nuclear fuel at a breakneck pace, shining millions of times brighter than ordinary stars. But because they consume their fuel so quickly, they also evolve much faster. After only a few million years, a blink of an eye in cosmic terms, they exhaust the hydrogen in their cores and move on to fusing heavier elements. As this happens, their outer layers become unstable, and powerful radiation pressure from the core begins to push material outward. The result is the violent mass loss that defines the Wolf-Rayet phase. In the case of the Pinwheel Star, this process has already stripped away its hydrogen-rich outer shell, exposing the hotter layers beneath. That's why the spectra of Wolf-Rayet stars are dominated not by hydrogen but by strong emission lines of helium, carbon, oxygen, and nitrogen, the byproducts of nuclear fusion. In other words, when we observe WR104, we're seeing a star that has peeled back its outer skin, revealing the nuclear furnace beneath. This is like looking at the beating heart of a giant, knowing that it won't beat much longer. The Wolf-Rayet stage is also important for another reason. It's a pre-supernova stage. Not every massive star becomes a Wolf-Rayet, but those that do are almost guaranteed to explode in a supernova when their cores collapse. The exact type of supernova depends on the star's mass, its rate of mass loss, and its chemical composition. For WR104, the expectation is that when its core finally gives way, it will erupt in a spectacular type IB or IC supernova, blowing its outer layers into space and leaving behind either a neutron star or a black hole. The winds from Wolf-Rayet stars don't just signal their impending doom, they also play a critical role in shaping the galaxy itself. The material blasted away is rich in heavy elements, forged in the star's core during nuclear fusion. Over time, this material mixes into the interstellar medium, seeding future generations of stars and planets with the ingredients needed for life. In fact, much of the carbon in your body likely came from ancient Wolf-Rayet stars that exploded long before our sun was born. In this sense, these dying giants are not just destroyers, they are creators, recycling matter and ensuring the continuity of cosmic evolution. WR104, the Pinwheel Star, is a textbook example of this stage. Its extreme winds, its stripped-down composition, and its violent outflows of dust and gas are all signs that it is nearing the end of its stellar life. The spiral dust plume we discussed earlier is a direct consequence of these winds colliding with the winds of its companion star. Without the Wolf-Rayet characteristics of WR104, the pinwheel pattern wouldn't exist. In other words, the beauty of the Pinwheel Star is inseparable from its destructive Wolf-Rayet nature. Astronomers study Wolf-Rayet stars not only because they're fascinating but also because they hold the key to understanding some of the most energetic events in the universe. Supernovae, gamma-ray bursts, and even black hole formation are all linked to this phase of stellar evolution. And since WR104 is relatively close to Earth and displays such a dramatic, observable structure, it has become a cornerstone case study for this entire class of stars. So when we say that the Pinwheel Star is a Wolf-Rayet star, we're saying that it's a massive, hot, unstable object, shedding its outer layers at incredible speeds, exposing its inner core, and preparing for a violent death. It's a stage of both destruction and creation, of breathtaking spectacle and inevitable collapse. The Wolf-Rayet stage is short-lived, just a few 100,000 years at most, but it is one of the most transformative moments in a star's life. And WR104 is living that moment right now, a ticking clock against the backdrop of the galaxy. When we talk about the Pinwheel Star, one crucial detail cannot be overlooked: it doesn't exist alone. WR104 is part of a binary star system, and this partnership is absolutely essential to its identity, its beauty, and its potential danger. Without its stellar companion, the Pinwheel Star would still be a Wolf-Rayet star, massive, hot, and unstable, but it wouldn't produce the breathtaking spiral pattern that earned it its nickname. To truly understand WR104, we have to understand the relationship it shares with its companion star. In the case of the Pinwheel Star, this process has already stripped away its hydrogen-rich outer shell, exposing the hotter layers beneath. That's why the spectra of Wolf-Rayet stars are dominated not by hydrogen but by strong emission lines of helium, carbon, oxygen, and nitrogen, the byproducts of nuclear fusion. In other words, when we observe WR104, we're seeing a star that has peeled back its outer skin, revealing the nuclear furnace beneath. This is like looking at the beating heart of a giant, knowing that it won't beat much longer. The Wolf-Rayet stage is also important for another reason. It's a pre-supernova stage. Not every massive star becomes a Wolf-Rayet, but those that do are almost guaranteed to explode in a supernova when their cores collapse. The exact type of supernova depends on the star's mass, its rate of mass loss, and its chemical composition. For WR104, the expectation is that when its core finally gives way, it will erupt in a spectacular type IB or IC supernova, blowing its outer layers into space and leaving behind either a neutron star or a black hole. The winds from Wolf-Rayet stars don't just signal their impending doom, they also play a critical role in shaping the galaxy itself. The material blasted away is rich in heavy elements, forged in the star's core during nuclear fusion. Over time, this material mixes into the interstellar medium, seeding future generations of stars and planets with the ingredients needed for life. In fact, much of the carbon in your body likely came from ancient Wolf-Rayet stars that exploded long before our sun was born. In this sense, these dying giants are not just destroyers, they are creators, recycling matter and ensuring the continuity of cosmic evolution. WR104, the Pinwheel Star, is a textbook example of this stage. Its extreme winds, its stripped-down composition, and its violent outflows of dust and gas are all signs that it is nearing the end of its stellar life. The spiral dust plume we discussed earlier is a direct consequence of these winds colliding with the winds of its companion star. Without the Wolf-Rayet characteristics of WR104, the pinwheel pattern wouldn't exist. In other words, the beauty of the Pinwheel Star is inseparable from its destructive Wolf-Rayet nature. Astronomers study Wolf-Rayet stars not only because they're fascinating but also because they hold the key to understanding some of the most energetic events in the universe. Supernovae, gamma-ray bursts, and even black hole formation are all linked to this phase of stellar evolution. And since WR104 is relatively close to Earth and displays such a dramatic, observable structure, it has become a cornerstone case study for this entire class of stars. So when we say that the Pinwheel Star is a Wolf-Rayet star, we're saying that it's a massive, hot, unstable object, shedding its outer layers at incredible speeds, exposing its inner core, and preparing for a violent death. It's a stage of both destruction and creation, of breathtaking spectacle and inevitable collapse. The Wolf-Rayet stage is short-lived, just a few 100,000 years at most, but it is one of the most transformative moments in a star's life. And WR104 is living that moment right now, a ticking clock against the backdrop of the galaxy. When we talk about the Pinwheel Star, one crucial detail cannot be overlooked: it doesn't exist alone. WR104 is part of a binary star system, and this partnership is absolutely essential to its identity, its beauty, and its potential danger. Without its stellar companion, the Pinwheel Star would still be a Wolf-Rayet star, massive, hot, and unstable, but it wouldn't produce the breathtaking spiral pattern that earned it its nickname. To truly understand WR104, we have to understand the relationship it shares with its companion star. Astronomers have determined that the Pinwheel Star's companion is a massive blue O-type star. These stars are some of the hottest and most luminous in the universe, shining tens of thousands of times brighter than the Sun. Their surface temperatures range between 30,000 degrees Celsius and 50,000 degrees Celsius, and they too unleash powerful stellar winds that blast into space at thousands of kilometers per second. In short, this is no ordinary star. It's another heavyweight in the cosmic ring, a stellar titan in its own right. The interaction between these two stars is what creates the extraordinary dynamics of the Pinwheel system. As both stars orbit each other roughly every 8 months, their gravitational embrace keeps them locked in a celestial dance. Each star hurls out torrents of particles, but instead of dissipating harmlessly into space, these stellar winds collide head-on in the region between them. Imagine two fire hoses aimed directly at each other, the jets of water slamming together and spraying outward in a chaotic but symmetrical pattern. Now scale that image up to a cosmic level, with winds of gas moving at thousands of kilometers per second, and you begin to picture what happens inside WR104's binary system. Where the winds of the Pinwheel Star and its blue companion meet, an extraordinary process unfolds. The colliding winds compress and cool the hot gas, allowing carbon-rich dust to condense and form. This is rare because dust has a difficult time forming in such extreme environments. Most stars are far too hot and energetic to allow solid particles to coalesce, but in this binary system, the collision zone provides just the right balance of pressure and temperature. From there, the orbital motion of the stars takes over, sweeping the newly formed dust outward in an elegant spiral that wraps around the system like the arms of a spinning pinwheel. This is why the binary nature of the Pinwheel Star is so essential. On its own, WR104 would still produce strong stellar winds, but those winds would expand outward in a chaotic, shapeless fashion. It's the presence of the companion star and the constant collision of their winds that impose order on the chaos, sculpting a near-perfect spiral that astronomers can actually observe across the vast gulf of 8,000 light-years. The relationship between the two stars is also critical to their evolution. Each star influences the other's fate. The Pinwheel Star, being a Wolf-Rayet, has already shed its hydrogen envelope and is barreling toward collapse. Its companion, though still burning hydrogen in its core, will likely follow a similar path in time, evolving into its own Wolf-Rayet star before eventually exploding. In some binary systems, the exchange of material between stars can even alter the timeline of these deaths. There's evidence that in certain close pairs, one star may siphon material from the other, effectively stealing fuel to extend its own life while hastening the demise of its partner. Whether this precise exchange is happening in WR104's system is still a matter of study, but what's clear is that the two stars are profoundly entangled in one another's destinies. The sheer scale of the binary system is another point of awe. Both stars are far larger and more massive than our Sun. WR104 is estimated to be at least 20 times the mass of the Sun, and its O-type companion could be even more massive. Combined, they form a system that dwarfs our solar system in energy output. And yet, despite their enormous power, the balance of their orbit is delicate enough to produce the breathtaking spiral dust plume with uncanny precision. Astronomers study binary systems like WR104 not only for their beauty but also for what they teach us about stellar evolution. Many of the most massive stars in the universe exist in binaries or even larger groups, rather than in isolation. These interactions can fundamentally change the star's life cycles and determine the types of supernovae or gamma-ray bursts they produce. In fact, some of the leading theories about long gamma-ray bursts, those intense, narrow beams of radiation that can travel across galaxies, suggest that they may originate in rapidly rotating Wolf-Rayet stars within binary systems. This makes the Pinwheel Star and its companion a kind of natural laboratory for testing our understanding of these extreme phenomena. And here's something even more intriguing. From Earth's perspective, it looks as though we're peering almost directly down the axis of this binary system. That vantage point is why the spiral structure is so clear to us. But it also raises one of the most chilling questions about WR104, whether its eventual supernova, and possibly a gamma-ray burst, might be aligned in our direction. If true, the consequences could be severe, even from 8,000 light-years away. We'll get to that scenario later, but for now, it's enough to note that the orientation of the Pinwheel Star's binary system is part of what makes it both scientifically invaluable and culturally captivating. The binary system is, in essence, the key to everything that makes the Pinwheel Star famous. Its spiral dust plume, its nickname, its scientific significance, and even its reputation as a doomsday star. Without the presence of that massive blue companion, WR104 would still be remarkable, but it wouldn't be the cosmic work of art we see today. The Pinwheel Star is not just one star, it's a duet, a partnership of giants, locked in an 8-month orbital waltz that sculpts beauty out of chaos and points us toward the mysteries of stellar death. If there's one feature that makes the Pinwheel Star stand out among the countless other stars scattered across the Milky Way, it's the extraordinary dust spiral that unfurls from its core like a cosmic whirlpool. This spiral isn't just a minor detail, it's the reason WR104 is called the Pinwheel Star, and it's one of the most visually striking natural phenomena ever observed in astronomy. To understand it is to glimpse the raw interplay of chaos and order on a galactic stage. At the heart of the system are the two massive stars, the Wolf-Rayet star WR104 itself, and its equally formidable blue O-type companion. Both stars are blasting out stellar winds, torrents of hot gas and charged particles rushing into space at millions of kilometers per hour. On their own, each wind would simply expand outward, scattering into the interstellar medium. But in a binary system like this one, the story becomes far more interesting. The winds crash into each other, and where they meet, shock fronts form, like invisible walls of compressed energy. These shock fronts act as the birthplace of the Pinwheel Star's dust. In the high-pressure zone where the winds collide, the gas cools rapidly, allowing carbon and other elements to condense into solid dust grains. This is no small achievement, because dust formation is actually rare in such extreme environments. Wolf-Rayet stars are so hot that their surroundings are usually hostile to solid particles. Yet in this narrow band of compressed material between the two stars, conditions become just right for dust to take shape. Now, add in the orbital motion of the two stars. They complete a full orbit around one another every 8 months or so. As they spin together, the dust being formed at the collision zone doesn't just disperse randomly, it gets swept outward in a spiral pattern, like water spraying from a rotating sprinkler. This is why the structure appears so elegant and ordered. With each orbit, another arm of the spiral is laid down, creating a continuous ribbon of dust winding away from the stars. Seen in infrared light, where astronomers can peer through the obscuring veil of interstellar dust, this spiral glows faintly against the backdrop of space. It looks astonishingly like a miniature galaxy, with the stars at the center acting as the galactic core and the spiraling dust arms mimicking the graceful sweep of a spiral galaxy's structure. Yet the scale, while vast by human standards, is only a fraction of what galaxies cover. The dust plume may extend for light years, but compared to the 100,000 light-year span of the Milky Way, it is still a tiny sculpture tucked inside our cosmic neighborhood. The comparison to a cosmic whirlpool isn't an exaggeration. The spiral is not just a two-dimensional shape, it's a three-dimensional flow of material winding through space, twisting outward in a way that can almost make you feel the motion when you look at it. Astronomers describe it as a rotating pinwheel, constantly renewing itself as fresh dust is created and pushed outward by the stellar winds. The spiral arms remain evenly spaced because the orbital dance of the stars is so regular, their rhythm almost mechanical. It's like a clockwork system in which the hands sweep around and leave trails of dust behind them, perfectly synchronized with each tick of the orbital clock. This spiral is more than beautiful, it's a scientific goldmine. By studying the spacing of the spiral arms, astronomers can calculate the orbital period of the stars. By measuring the brightness of the dust in infrared, they can estimate how much material the stars are shedding into space. The spiral is a record of stellar behavior, a cosmic logbook written not in words but in ribbons of dust. Every curl of the spiral tells us something about how the stars interact, how they evolve, and how they shape their surroundings. But the spiral also sparks something deeper: wonder. When the first detailed infrared images of WR-104's spiral were released in the late 1990s, they captivated both scientists and the public. To the human eye, the structure looks almost too perfect to be natural, like an artist's rendering rather than a product of physics. It is symmetry born out of chaos, an exquisite balance between violence and beauty. The Pinwheel Star doesn't just shine, it creates art in the void of space, sculpting matter into a form that resonates with our sense of harmony. What makes it even more awe-inspiring is the scale. The spiral arms of dust stretch across trillions of kilometers. If you placed our entire solar system inside the spiral, it would disappear within just a fraction of its structure. Imagine the Earth orbiting peacefully inside the vast arcs of dust, dwarfed into insignificance by the forces at play. That's the kind of raw power and majesty we're dealing with here. And yet, this whirlpool is not permanent. Over thousands of years, the dust spirals outward into the interstellar medium, gradually diffusing and blending into the galaxy. Each arm of the pinwheel is temporary, destined to fade into the darkness as new arms take its place. The spiral is alive, in constant motion, a work in progress painted across the canvas of the universe. The dust spiral of the Pinwheel Star is one of those cosmic structures that remind us just how strange and magnificent the universe can be. It is at once violent and serene, destructive and creative. The Wolf-Rayet star is tearing itself apart, shedding its mass in furious winds, and yet from this destruction comes something breathtakingly beautiful, a cosmic whirlpool spinning silently in the darkness, visible to us from across 8,000 light-years. The story of how the Pinwheel Star came to capture our imagination begins, like so many great tales in astronomy, with a discovery that at first seemed ordinary but soon revealed itself to be extraordinary. WR-104, as it was originally catalogued, wasn't discovered because someone looked up at the night sky and immediately noticed something unusual. To the naked eye, the star doesn't stand out at all, it's too faint and too far away. It only became known to astronomers because of the meticulous surveys and catalogues that classify stars by their spectral fingerprints. The WR in WR-104's name comes from the Wolf-Rayet catalogue, a collection of rare, massive stars that display the distinctive emission lines of helium, nitrogen, carbon, and oxygen in their spectra. These stars had first been identified in the 19th century by astronomers Charles Wolf and Wolf-Rayet, who noticed that a handful of stars had unusually broad emission lines instead of the absorption lines seen in ordinary stars. WR-104 entered this catalogue in the 20th century as astronomers systematically worked their way across the sky, identifying and recording Wolf-Rayet stars wherever they could find them. At first, WR-104 was simply one of many. There was nothing to suggest it was unique, just another hot, massive star in the constellation Sagittarius, about 8,000 light-years away. But that changed in the 1990s, when astronomers began turning more sophisticated instruments toward it. The breakthrough came with the use of infrared interferometry, a powerful technique that combines the light from multiple telescopes to create a sharper, higher-resolution image than a single telescope could produce on its own. In 1998, a team led by Peter Tuthill, John Monnier, and William Dankai used the Keck telescope in Hawaii, one of the most powerful observatories in the world, to observe WR-104 in unprecedented detail. What they found stunned them. Instead of appearing as a simple point of light, the star system revealed a spectacular spiral plume of dust, winding outward like the blades of a fan or the arms of a pinwheel. It was one of the first times astronomers had ever seen such a clear, structured spiral around a star system. The discovery was so striking that it quickly made its way beyond the scientific community into popular media. The images looked almost artistic, resembling a glowing cosmic whirlpool frozen in motion. For astronomers, this wasn't just pretty, it was scientifically profound. It confirmed that the binary nature of WR-104, with its colliding stellar winds, could produce a highly organized and symmetrical dust structure visible even from thousands of light-years away. In the years that followed, WR-104 became a frequent target for study. Infrared imaging continued to refine our view of its spiral, while spectroscopic analysis helped confirm the composition of the dust and the properties of the two stars at the system's core. The orbital period of about 8 months was calculated by studying the rotation of the spiral, and this provided one of the clearest demonstrations of how binary star dynamics could directly sculpt large-scale structures in space. The discovery also sparked broader interest because of its implications. When scientists realized that we might be looking nearly straight down the axis of WR-104's rotation, speculation grew that if the star were to collapse into a supernova and unleash a gamma-ray burst, that burst could be aimed in our direction. Suddenly, WR-104 wasn't just a curiosity, it was a potential doomsday star, a subject of both fascination and fear. While further research has suggested that the actual risk to Earth is very low, this possibility ensured WR-104 a lasting place in public imagination. One of the most remarkable aspects of WR-104's discovery is how it illustrates the power of technological advancement. Before the development of interferometry and advanced infrared imaging, the spiral would have remained invisible. The star would still be catalogued as just another Wolf-Rayet object, tucked away in the constellation Sagittarius with little fanfare. It was only by pushing the boundaries of observational astronomy that scientists could reveal the hidden artistry of this cosmic system. Since then, WR-104 has been compared to other Wolf-Rayet binaries that also produce dust, but few come close to its level of symmetry and visibility. The Pinwheel Star remains one of the most photogenic Wolf-Rayet systems ever discovered, and its discovery has become a cornerstone example in both scientific research and science communication. Whenever astronomers want to illustrate the interplay between massive stars and their environments, WR-104 is often the go-to image. In the end, the discovery of the Pinwheel Star was more than just adding another entry to a catalogue. It was a revelation, a reminder that the universe is capable of creating beauty on a scale that defies imagination, and that sometimes the most ordinary-looking stars hide the most extraordinary secrets, waiting for the right tools to bring them into focus. When we talk about the Pinwheel Star, one of the hardest things to truly grasp is just how enormous and extreme it is compared to the familiar star we know best, our Sun. The Sun might feel unimaginably huge when you look at it in the sky, knowing that 1,000,000 Earths could fit inside it. But in the grand hierarchy of stars, the Sun is actually quite ordinary, even small, when compared with monsters like WR-104. Let's start with mass, because in astronomy, mass dictates almost everything about a star's life cycle. Our Sun is a G-type main sequence star, weighing in at about 1 solar mass, the baseline unit astronomers use to compare other stars. WR104, on the other hand, is estimated to be at least 20 times the mass of the Sun, possibly more. That doesn't just mean it's 20 times bigger. It means its gravity, its energy output, and the pressure in its core are on an entirely different level. Its blue O-type companion is no lightweight either, likely weighing in at 25 to 30 solar masses. Together, this binary system contains more than 50 times the mass of our Sun. In terms of physical size, the comparison becomes even more striking. The Sun's radius is about 700,000 kilometers. WR104, despite shedding much of its outer material in the Wolf-Rayet stage, still swells to several times the Sun's radius. Some estimates suggest that its size could stretch up to 5 to 10 times the Sun's diameter. If you place the Pinwheel Star at the center of our solar system, it would easily extend well past the orbit of Mercury, possibly even approaching Venus's path depending on its current stage of contraction or expansion. The O-type companion, in its own right, could be anywhere from 8 to 15 times the radius of the Sun. But perhaps the most mind-blowing comparison comes from luminosity. Our Sun produces a steady, life-sustaining glow that seems powerful to us, but it is merely modest compared to stars like WR104. The Pinwheel Star blazes with a luminosity tens of hundreds of thousands of times greater than the Sun. Its companion adds even more brilliance. This means that in a single second, WR104 outputs more energy than our Sun produces in days, or even weeks. If WR104 were magically transported to the center of our solar system, the effects would be catastrophic. The sheer radiation would instantly boil away Earth's oceans, strip away its atmosphere, and vaporize life as we know it. Planets at Earth's distance would be scorched barren in an instant. Even Jupiter, far beyond Earth's orbit, would not be safe from the extreme heat and radiation. It's a reminder that our Sun, while powerful to us, is a calm and stable star compared to the raging furnace that is WR104. Another way to appreciate the scale is to think in terms of the dust spiral itself. Each arm of the spiral stretches out across distances measured in astronomical units, AU, the distance between the Earth and the Sun. The spiral arms can span dozens, even hundreds of AU. Our solar system, with its planets neatly orbiting within about $30 of the Sun, would look like a tiny pocket inside just one of WR104's vast swirling dust ribbons. It's humbling to imagine how small our entire planetary system would seem if set against the backdrop of the Pinwheel Star's spiral structure. It's also important to emphasize the difference in timescales. The Sun is a relatively patient star, expected to live for about 10 billion years in total, and right now it's only about halfway through that lifespan. In contrast, a star like WR104, with its enormous mass and blazing luminosity, burns through its fuel in only a few million years. It lives fast and dies young. The Sun is a marathon runner, pacing itself over billions of years, while WR104 is more like a sprinter, exhausting itself in a burst of intensity that ends in spectacular destruction. When you compare WR104 to the Sun, you begin to see the vast diversity of stars in our galaxy. On one end, you have small red dwarfs, tiny, dim stars that can burn for trillions of years. In the middle, you have stable stars like our Sun. And on the extreme end, you have giants like the Pinwheel Star, which dwarf our Sun in every sense: mass, size, brightness, and energy output. These extremes help shape the galaxy, because it's the massive stars that drive cosmic evolution through their violent winds, their dust spirals, and eventually their explosive deaths. The sheer scale of WR104 is part of what makes it so captivating. It's not just bigger than the Sun, it's in a completely different league. Its mass, its luminosity, and its dust spiral remind us that our solar system, while precious to us, is just one tiny corner of a much larger, more violent, and more breathtaking universe. And the Pinwheel Star, with all its grandeur, is a perfect symbol of that cosmic scale. When it comes to the temperature and brightness of the Pinwheel Star, the numbers almost defy imagination. To grasp just how extreme WR104 is, we need to think about the energy it radiates every single second and the fiery heat that drives its incredible luminosity. These properties are not just incidental, they are the defining features of a Wolf-Rayet star nearing the end of its life. Let's begin with temperature. Our Sun's surface temperature hovers around 5,500 degrees Celsius, hot enough to produce visible light and sustain life on Earth. It's blistering by human standards, but it pales in comparison to the Pinwheel Star. WR-104's surface temperature is estimated to exceed 40,000 degrees Celsius, more than 7 times hotter than the surface of our Sun. And that's just the lower boundary of estimates. Many Wolf-Rayet stars are known to reach surface temperatures upwards of 100,000 degrees Celsius. At these extreme levels, the star emits most of its radiation not in the visible spectrum, but in the ultraviolet. This is why Wolf-Rayet stars shine so intensely when observed through instruments sensitive to higher energy wavelengths. The consequences of such heat are dramatic. The star's radiation pressure is so powerful that it blows away its outer layers in massive stellar winds, stripping the star of its hydrogen envelope and exposing its hotter inner layers. These winds stream outward at thousands of kilometers per second, carrying material far into space. That very outflow of energy and matter is what allows the spiral dust plume of the Pinwheel Star to exist. So the extreme temperature of WR-104 is not just a statistic, it is the very engine behind its spectacular pinwheel pattern. Now let's turn to brightness, or more accurately, luminosity. Luminosity is a measure of the total energy a star emits per second across all wavelengths of light. Our Sun provides a useful baseline. It emits about 3.8x10 squared watts of energy. That's an almost incomprehensible figure, yet WR-104 dwarfs it. Estimates suggest that the Pinwheel Star shines with a luminosity hundreds of thousands of times greater than the Sun. Combine that with its massive blue O-type companion, which is itself tens of thousands of times more luminous than the Sun, and you have a binary system that blazes like a beacon, visible across thousands of light-years. To put it in perspective, if WR-104 were somehow placed at the same distance from Earth as the Sun, the sky wouldn't just be bright, it would be utterly uninhabitable. The sheer flood of energy would incinerate everything in moments. Even from thousands of light-years away, WR-104's luminosity is detectable with relative ease, which tells you just how much energy it's pumping into the galaxy. Another way to think of its brightness is in terms of magnitude, the system astronomers use to measure how bright a star appears from Earth. WR-104 is faint to the naked eye because of its distance and the interstellar dust in Sagittarius, but intrinsically it is a powerhouse. If you stripped away the distance and intervening material, it would outshine almost every star in the night sky. In fact, Wolf-Rayet stars like WR-104 are among the brightest known stars in the universe, burning through their nuclear fuel at staggering rates to sustain their brilliance. This extreme brightness comes at a cost. A star's luminosity is directly tied to how quickly it consumes its nuclear fuel. The Sun, with its modest output, conserves hydrogen in its core and stretches its lifespan to about 10 billion years. WR-104, with its colossal brightness, is burning through its reserves in just a few million years. Its brilliance is a double-edged sword, spectacular to observe, but the very reason why the star's life will be cut tragically short. The combination of blistering surface temperature and overwhelming luminosity makes WR-104 one of the most intense stars known. It doesn't just shine, it dominates its environment. Its ultraviolet radiation ionizes nearby gas, its stellar winds sculpt surrounding dust, and its binary dance with its O-type companion creates the iconic spiral we see. WR-104 is a furnace, a lighthouse, and an artist all at once, blazing with a ferocity that both fascinates and humbles us. It's worth noting, too, that WR-104 is only one example of a broader class of Wolf-Rayet stars, many of which display even higher temperatures and luminosities. Yet WR-104 remains iconic because its unique spiral dust plume allows us to visualize the effects of that heat and brightness in a way that no other system quite matches. It is, quite literally, a living example of how extreme stellar physics creates beauty in the cosmos. So when we speak of the Pinwheel Star's surface temperature being over 40,000 degrees Celsius and its luminosity being hundreds of thousands of times that of the Sun, we're not just quoting numbers. We're describing a star that burns with unimaginable intensity, a cosmic powerhouse on the edge of collapse, and a symbol of both the fury and the artistry of stellar evolution. The question of life expectancy is where the story of the Pinwheel Star becomes both awe-inspiring and sobering. Stars, like living creatures, have life cycles: birth, maturity, and ultimately, death. But unlike the billions of years our Sun will enjoy as a steady main sequence star, Wolf-Rayet stars such as WR-104 are destined to live fast and die young. Their immense size and explosive energy output make them some of the shortest-lived stars in the universe, even though they shine the brightest while they last. Let's put this into context. Our Sun is about 4.6 billion years old and is expected to continue burning steadily for another 5 billion years or so before it expands into a red giant and eventually becomes a white dwarf. That's a total lifespan of roughly 10 billion years, an unimaginably long stretch of cosmic time. By contrast, WR-104's entire existence from birth to death will last only about 5 million years. To us, that's still an enormous number, but in the timescale of stars, it's the blink of an eye. Why is this lifespan so short? It comes down to mass. The more massive a star is, the faster it burns through its nuclear fuel. WR-104, with a mass more than 20 times greater than the Sun, burns at a temperature over 40,000 degrees Celsius and radiates hundreds of thousands of times more energy. That kind of brilliance requires an astronomical rate of fuel consumption. Instead of sipping gently at its hydrogen like the Sun, WR-104 gulps it down in a cosmic frenzy. The Pinwheel Star has already passed the long, stable phase of life known as the main sequence, when a star fuses hydrogen into helium at its core. In its younger days, WR-104 would have been an O-type blue giant, already incredibly hot and bright. But that stage was fleeting. Now, as a Wolf-Rayet star, it has exhausted much of its core hydrogen and is fusing heavier elements. It stripped away its hydrogen envelope, exposing deeper layers of helium and other elements. The furious stellar winds that blow off its surface are a sign of this instability. WR-104 is shedding itself into space, atom by atom, as it marches toward its inevitable end. This stage, the Wolf-Rayet phase, is essentially the final chapter in the life of a massive star. It doesn't last long. Astronomers estimate that the Wolf-Rayet stage endures for only a few 100,000 years at most. That's a brief moment when measured against the cosmic clock. WR-104 is already here, already blazing with the characteristics of a dying star. That tells us its time is almost up, cosmically speaking. But almost up in astronomy doesn't mean tomorrow. The star is about 8,000 light-years away, so what we see is actually WR-104 as it was 8,000 years ago. It could explode tomorrow, or it could take another hundreds of thousands of years. Either way, WR-104 is firmly in its terminal stage of evolution. Its fate is sealed. It will not quietly fade into obscurity like a smaller star. Instead, it is destined to end in a cataclysmic explosion. The short lifespan of WR-104 also illustrates why massive stars are rare in the galaxy. At any given time, far fewer massive stars exist compared to ordinary stars like the Sun. Not because they don't form, but because they burn out so quickly. There could be dozens of small stars being born for every massive star like WR-104 that dies. It's a cosmic case of quality over quantity. The most massive stars give us the most spectacular displays, but they vanish from the stage much too soon. And yet, in their brevity, they leave behind a profound legacy. The materials hurled into space by massive stars in their deaths, carbon, oxygen, nitrogen, and heavier elements, become the raw ingredients for new stars, new planets, and ultimately life itself. The very atoms in our bodies were forged in the hearts of stars that lived short, furious lives before scattering their ashes across the cosmos. WR-104 is another such star, preparing to return its essence to the galaxy. So when we consider the life expectancy of the Pinwheel Star, we see both tragedy and beauty. Its brilliance is unsustainable. Its end is inevitable. But in that end lies renewal, because stars like WR-104 are the universe's way of recycling matter and energy, seeding the galaxy with the building blocks of tomorrow. It may be nearing the end of its life, but in dying, it will enrich the cosmos for generations of stars yet to come. The fate of the Pinwheel Star is not a quiet one. Astronomers are almost certain that WR-104 will not simply fizzle out like smaller stars do. Instead, it will end its life in a blaze of cosmic fury, a supernova. This expectation is rooted in our deep understanding of stellar evolution, particularly for massive stars like WR-104, which burn so brightly and live so briefly. Let's first understand what a supernova is. A supernova is one of the most energetic and violent events in the universe, the death cry of a massive star. When a star at least 8 times the mass of the Sun exhausts its nuclear fuel, it can no longer generate the pressure needed to counteract the crushing force of gravity. Its core collapses in a fraction of a second, unleashing a shockwave that rips through the star's outer layers and blasts them into space at incredible speeds. The explosion outshines entire galaxies for weeks or months, releasing as much energy in a single event as our Sun will produce over its entire 10 billion-year life. WR-104, with a mass at least 20 times that of the Sun, checks every box for a supernova candidate. It has already burned through its hydrogen and is fusing heavier elements in its core. Its outer layers are being stripped away by powerful winds, leaving behind a hot, unstable core. At some point, whether it's tomorrow or in 100,000 years, the star will run out of fuel altogether. When that happens, gravity will win. The core will collapse, and the Pinwheel Star will explode. This isn't speculation, it's astrophysical certainty. Wolf-Rayet stars don't quietly fade into white dwarfs like the Sun will. They are too massive, too unstable, and too energetic. Their destiny is violent, and WR-104 is no exception. Astronomers expect it to go supernova, and when it does, it will be a spectacular event even from 8,000 light-years away. To give you a sense of scale, if WR-104 exploded in a supernova, it would likely shine as brightly as the full moon in our sky, even though it's thousands of light-years distant. It would be visible in broad daylight and dominate the night sky for weeks or months. Historical records show that humanity has witnessed supernovae before, such as SN 1054, which created the Crab Nebula and was bright enough to be seen in the daytime sky for nearly 2 years. WR-104 supernova would be at least as dramatic, a once-in-many-lifetime spectacle. But beyond the spectacle lies the science. Supernovae are not just fireworks, they are engines of creation. In the death of a star like WR-104, heavy elements such as iron, gold, and uranium are forged and cast into space. Without supernovae, the universe would lack the diversity of elements needed for planets, oceans, and even life. The Pinwheel Star's death will be a catastrophic loss for itself, but a tremendous gift to the galaxy, a recycling of cosmic matter that may one day form new solar systems, perhaps even new Earth-like worlds. There's also the question of what will be left behind after WR-104 explodes. For stars of its size, the collapse of the core typically results in the formation of either a neutron star or a black hole. Given WR-104's mass, many astronomers suspect it could collapse directly into a black hole, one of the most mysterious and extreme objects in the universe. If that happens, the Pinwheel Star's final act would not only scatter elements across space but also create a gravitational monster that bends space-time itself. For now, we can only wait. The timescale of astronomy is vast, and though WR-104 is in its final act, we may never witness its explosion. Or, it could happen within our lifetimes. That uncertainty is part of what makes the Pinwheel Star so captivating. It is a cosmic ticking clock, a reminder that stars, like all things, have lifespans, and that their endings can be both terrifying and profoundly beautiful. So, when astronomers say WR-104 will end in a supernova, it's not a question of if, it's a question of when. And when it does, the Pinwheel Star will put on a show for the galaxy, an eruption of energy and matter that will outshine almost everything else in the night sky. It will mark the end of one star's story, but also the beginning of countless others, as its remnants seed the cosmos with the building blocks of the future. When we talk about the Pinwheel Star's eventual death in a supernova, that alone is awe-inspiring enough. But there is an even more dramatic, and far scarier, possibility tied to WR-104's fate, the chance that it could unleash a gamma-ray burst, GRB. While supernovae are common in the life cycles of massive stars, gamma-ray bursts are rare, extreme, and profoundly destructive events. And WR-104, because of its mass, rotation, and possible alignment, is a candidate for producing one. A gamma-ray burst is essentially the most powerful type of explosion known in the universe. There are different kinds, but the most energetic are the so-called long-duration gamma-ray bursts, which last from a few seconds to several minutes. They are thought to occur when a massive, rapidly rotating star collapses into a black hole. As it collapses, the material falling inward forms an accretion disk around the newborn black hole. Magnetic fields and angular momentum then funnel some of that infalling material outward in the form of ultra-relativistic jets, narrow beams of energy moving close to the speed of light. These jets break through the star's outer layers and shoot out into space, releasing more energy in a brief flash than the Sun will radiate in its entire lifetime. Now, here's where WR-104 comes into the picture. As a Wolf-Rayet star, it has many of the conditions associated with GRB progenitors. It's massive enough to collapse directly into a black hole. It has lost its outer hydrogen envelope, which is a key ingredient in producing the clean channels necessary for gamma-ray jets to form. And crucially, its rapid rotation may provide the angular momentum needed to power those jets. All of these factors place WR-104 firmly on the shortlist of stars that could end their lives not only in a spectacular supernova but also in a long gamma-ray burst. The frightening part is not just the possibility of WR-104 producing a GRB, it's the fact that GRBs are highly directional. Unlike a supernova, which radiates energy in all directions, a gamma-ray burst fires most of its destructive power in two extremely narrow beams, aligned with the star's rotational axis. If one of those beams were aimed directly at Earth, the consequences would be catastrophic. The destructive potential of a GRB comes from its sheer intensity. A GRB occurring within a few thousand to tens of thousands of light-years could strip away Earth's ozone layer, exposing the planet to lethal levels of solar and cosmic radiation. This wouldn't necessarily vaporize the planet, but it could devastate the biosphere, triggering mass extinctions. Some scientists even speculate that past mass extinction events on Earth may have been linked to nearby gamma-ray bursts. For WR-104, the possibility of a GRB is what transformed it from an astronomer's curiosity into a doomsday star in the public imagination. When Peter Tuthill and colleagues first revealed images of WR-104's pinwheel spiral in the late 1990s, they noted that it appeared we might be looking straight down the star's axis of rotation. That immediately raised alarm. If the rotation axis is indeed aligned with Earth, and if WR-104 produces a GRB when it dies, then our planet could be right in the line of fire. To be clear, the likelihood of this scenario is extremely small, and later studies suggest that the alignment may not be as perfect as it initially appeared. Still, the very fact that WR-104 ticks so many boxes for being a potential GRB progenitor makes it both fascinating and unnerving. It's important to note, too, just how rare GRBs are. Even among Wolf-Rayet stars, only a fraction produce them. The combination of mass, rotation, metallicity, and orientation has to be just right. But WR-104 stands as one of the few nearby stars that fits the profile closely enough to warrant serious consideration. That's why astronomers continue to study it carefully, using infrared observations, spectroscopic analysis, and computer simulations to refine our understanding of its structure and its future. So when we talk about WR-104's gamma-ray burst potential, we're entering the realm of the most extreme astrophysical events in existence. It's not just about a star dying, it's about the possibility of a star firing a focused, unimaginably powerful beam of energy directly across the galaxy. It's a scenario that combines both the fragility of life on Earth and the vast, indifferent forces of the cosmos. In the end, WR-104 may never produce a GRB at all, or if it does, its jets may be angled safely away from us. But the possibility alone is enough to keep scientists and the public alike captivated. It reminds us that while the universe creates breathtaking beauty, like the Pinwheel Star's spiral dust plume, it also harbors the potential for unimaginable violence. And WR-104, perched on the edge of its explosive destiny, embodies both sides of that cosmic truth. To truly appreciate why the Pinwheel Star inspires both fascination and unease, we need to pause and look closely at the very phenomenon that makes it so infamous in the first place, the gamma-ray burst, or GRB. These bursts are, without exaggeration, the most powerful explosions known to science. Supernovae themselves are breathtakingly energetic, but GRBs go even further. They are the ultimate cosmic fireworks, releasing unimaginable amounts of energy in fleeting moments that can reshape entire regions of space. A gamma-ray burst is essentially a flash of extremely high-energy radiation, dominated by gamma rays, the most energetic form of electromagnetic radiation. Gamma rays make X-rays look gentle by comparison. They carry so much energy that even a brief dose can tear apart molecules and strip atoms of their electrons. When astronomers detect a GRB, they're seeing the most violent outpouring of energy the universe can produce, often from billions of light-years away. What makes GRBs extraordinary is their sheer intensity. In just a few seconds to a few minutes, a single GRB can release more energy than our Sun will emit over its entire 10 billion-year lifetime. Imagine condensing all the energy of every star in our galaxy into a single moment. That begins to hint at the scale of these cosmic events. There are two main types of gamma-ray bursts. 1. Short-duration GRBs, lasting less than 2 seconds, usually thought to be caused by the collision of compact objects like neutron stars or black holes. 2. Long-duration GRBs, lasting several seconds to a few minutes, and these are the kind most relevant to WR104. Long GRBs are linked to the deaths of massive, rapidly rotating stars that collapse into black holes, unleashing jets of energy along their rotational axes. When one of these bursts happens, it can be detected across vast stretches of the cosmos. Many of the GRBs we've observed originate from galaxies billions of light-years away, yet their radiation still reaches us strongly enough to be picked up by satellites like NASA's Swift or Fermi observatories. That's how bright they are, shining across a significant fraction of the observable universe. But what really sets gamma-ray bursts apart is their directionality. Unlike supernovae, which spread their energy relatively evenly in all directions, GRBs concentrate their fury into two narrow beams or jets. This makes them even more intense. If you're in the path of a jet, you see an explosion far brighter and deadlier than the same event viewed off to the side. It's like the difference between standing under a sprinkler versus standing in front of a fire hose. And that's why alignment matters so much in the case of WR104. To put it in human terms, if a GRB were aimed directly at Earth from within a few thousand light-years, it could deliver enough radiation to strip away the ozone layer, irradiate the surface, and trigger global ecological collapse. It wouldn't necessarily destroy the planet itself, but it could sterilize life as we know it. Fortunately, such events are exceedingly rare on the timescales of human civilization. Gamma-ray bursts are also central to modern astrophysics because they give us clues about the life cycles of massive stars, the formation of black holes, and even the structure of the early universe. Some of the most distant objects ever observed are GRBs, their brilliant flashes serving as cosmic beacons from the dawn of time. In fact, GRBs are so powerful that they've become tools for probing the universe itself, helping astronomers study galaxies that would otherwise be invisible. So when we say WR104 could one day produce a GRB, we're talking about the possibility of it unleashing the most extreme type of explosion the universe has to offer. It's not just a supernova, it's potentially a supernova with a focused death beam, a cosmic sniper shot of energy traveling across light-years. In short, gamma-ray bursts are the epitome of both the awe and the terror of astrophysics. They are dazzling reminders of the power of nature on scales we can barely comprehend, and they are also stark reminders of the vulnerability of life in the face of such forces. And the Pinwheel Star, sitting quietly in Sagittarius, is a candidate for joining the ranks of stars that unleash this ultimate spectacle. One of the reasons the Pinwheel Star has captured so much public attention is not just its beauty, or even its eventual death as a supernova, but the unnerving possibility that it might be aimed directly at us when it goes out with a bang. This is the heart of the alignment concerns surrounding WR104, the idea that its rotational axis, the very axis along which a potential gamma-ray burst would fire, could be pointing almost straight at Earth. This worry traces back to the 1990s, when Peter Tuthill and his colleagues produced the first high-resolution images of WR104's spiral dust plume using interferometry at the Keck Observatory. Those images revealed the now famous pinwheel pattern, a perfect spiral of dust winding outward into space. But more than just a pretty picture, that spiral gave astronomers clues about the orientation of the system. From the perspective of Earth, we appear to be looking directly down onto the spiral, as if staring into the center of a cosmic whirlpool. That suggested that WR104's rotational axis might be aligned very closely with our line of sight. Why does that matter? Because if WR104 produces a gamma-ray burst when it dies, the beams of radiation would emerge along its rotational axis. If Earth lies anywhere within that narrow cone, we could be exposed to one of the most destructive phenomena the universe can unleash. The spiral structure doesn't just hint at beauty, it might also be a warning sign about where those jets would point. The potential consequences are what first fueled WR104's reputation as a doomsday star. If a GRB were fired directly at Earth from 8,000 light-years away, it could strip away the ozone layer, leaving the planet vulnerable to ultraviolet radiation from the sun. It could also directly irradiate the surface, leading to a cascade of ecological collapses. Some scientists even speculate that past mass extinctions in Earth's history may have been triggered by distant GRBs. The thought that WR-104's axis might be pointing at us understandably raised alarm. But as with so many things in astronomy, appearances can be deceptive. The pinwheel spiral looks perfectly face-on, but interpreting that geometry across such vast distances is tricky. Later studies have suggested that while the spiral might appear aligned, the actual rotational axis of the Wolf-Rayet star and its companion could be tilted at an angle. Even a small tilt would spare Earth from being in the direct line of fire of a gamma-ray burst. After all, the jets are incredibly narrow, perhaps just a few degrees across, so the difference between devastation and safety could come down to a seemingly minor misalignment. The alignment concern remains an open question because of the limitations of our observations. Measuring orientation precisely from 8,000 light-years away is notoriously difficult. Dust obscuration, the complexity of binary interactions, and the limitations of our instruments all add uncertainty. Still, the possibility lingers, and that's what makes WR-104 such an intriguing mix of beauty and danger. Astronomers often stress that even if WR-104 is aligned perfectly with Earth, the odds of a gamma-ray burst occurring are low, and the timescale makes it even less likely to affect us in any meaningful sense. But the very fact that we might be looking directly down the barrel of a cosmic gun has been enough to cement WR-104 in popular culture as the archetypal threat star. In a way, the alignment concern tells us more about human psychology than it does about astrophysics. There are countless Wolf-Rayet stars in the galaxy, many of them capable of ending in GRBs, but WR-104 has become famous because we happen to see it face-on. It's like standing in front of a cannon that may or may not be loaded, knowing that it might go off in the next 1,000 years, or the next 100,000. The risk is vanishingly small, but the imagery is powerful. So, alignment remains one of the great questions surrounding WR-104. Are we staring directly into the axis of a future gamma-ray burst, or is the geometry deceiving us? For now, the evidence leans towards safety, but the mystery continues to fuel both scientific inquiry and public fascination. If the Pinwheel Star were to unleash a gamma-ray burst, GRB, and one of its jets happened to be aimed directly at Earth, the consequences would be nothing short of catastrophic. Unlike a nearby supernova, which might dazzle us with a bright display but wouldn't cause lasting damage at WR-104's distance of 8,000 light-years, a GRB is an entirely different beast. Because its energy is concentrated into narrow, high-energy beams, a gamma-ray burst has the power to reach across that vast distance and still wreak havoc on our planet. The first and most immediate effect would be on Earth's atmosphere. Our ozone layer, the shield that protects us from the sun's ultraviolet radiation, is particularly vulnerable to gamma rays. A strong enough burst could strip away large portions of this protective layer in a matter of seconds. Without the ozone to block harmful radiation, Earth's surface would be bombarded with ultraviolet light, sterilizing vast stretches of the biosphere and drastically increasing cancer rates in surviving organisms. But the damage wouldn't stop there. High-energy photons from a GRB would interact with atmospheric molecules, breaking them apart and creating nitric oxides. These compounds would not only destroy ozone further but could also lead to a chemical cascade, cooling the climate in the short term and potentially altering global weather patterns. A sudden gamma-ray winter could follow, reducing temperatures, disrupting ecosystems, and collapsing food chains. The biosphere would feel the brunt of it. Plants and phytoplankton, which rely on stable sunlight and balanced radiation, would suffer immediate declines. Phytoplankton in particular are the foundation of oceanic food webs, producing much of Earth's oxygen and serving as the base of the marine food chain. If they were decimated, the ripple effects through the oceans and atmosphere would be profound. On land, ultraviolet radiation would scorch unprotected organisms, likely leading to widespread extinctions. It's not hard to imagine the outcome, a mass extinction event. In fact, some researchers have proposed that past die-offs in Earth's history may have been caused by gamma-ray bursts. One candidate is the Ordovician-Silurian extinction around 450 million years ago, when roughly 85% of marine species disappeared. Some scientists suggest that a GRB from a nearby Wolf-Rayet star could have stripped the ozone layer, triggering a collapse in marine life and reshaping the course of evolution. The sheer scale of energy in a GRB makes it difficult to overstate the devastation. A gamma-ray burst directed at Earth from WR-104's distance would release more energy into our planet's atmosphere than the detonation of billions of nuclear bombs. The irony, however, is that we wouldn't see fire raining from the sky or continents vaporizing. The destruction would be quieter, almost invisible, an invisible flood of radiation unraveling the systems that sustain life. And unlike an asteroid impact or volcanic supereruption, a GRB gives no warning. The burst would arrive at the speed of light, meaning by the time we detected it, the damage would already be underway. In essence, if WR-104 were aligned with Earth and produced a GRB, there would be no defense. Humanity would have no shield and no time to prepare. That's the chilling part of contemplating the Pinwheel Star's potential. Its beauty is mesmerizing, the spiral dust plume, the glowing energy, the perfect pinwheel pattern, but hidden inside is the possibility of a cosmic weapon aimed unknowingly at us. The contrast between appearance and potential danger is what makes WR-104 such a compelling mystery. Thankfully, most astronomers reassure us that the odds of this doomsday scenario are exceedingly small. But thinking about what it would mean if it did happen helps us understand the raw scale of cosmic forces. It humbles us, reminding us that Earth and all its life are fragile in the face of the universe's power. After painting such a dire picture of what a gamma-ray burst from the Pinwheel Star could mean for Earth, it's absolutely essential to step back and breathe a sigh of relief. Because here's the truth, the odds of WR-104 posing any real danger to our planet are astronomically low. In fact, scientists consistently stress that we do not need to panic about this star. First, let's revisit the alignment issue. While early observations gave the eerie impression that we're staring straight down the barrel of WR-104's potential gamma-ray burst jets, later research has introduced much more uncertainty. The spiral dust plume may look like it's face-on, but that doesn't guarantee the star's rotational axis is perfectly aligned with Earth. Even a tilt of just a few degrees would ensure that the beam of a GRB, if one even occurs, would miss us entirely. Considering that the beam is only a couple of degrees wide, the odds of a direct hit are already extremely small. Second, let's talk about distance. WR-104 is about 8,000 light-years away. That may sound uncomfortably close in astronomical terms, but it's still a vast gulf of space. To put it in perspective, the nearest star to Earth, Proxima Centauri, is just over 4 light-years away. WR-104 is 2,000 times farther than that. At such a distance, a regular supernova from WR-104 would pose no danger to us at all. It would simply be a spectacular light show in the sky. Only the very narrow, ultra-energetic beam of a GRB could cross that distance in a way that might matter. Third, not all Wolf-Rayet stars produce gamma-ray bursts when they die. While many are considered candidates, a GRB requires a very specific set of conditions. The star must be rotating rapidly, it must collapse in a certain way, and the jet must be launched along just the right axis. Even among massive stars, GRBs are rare. In fact, scientists estimate that only about 1 in 100 Wolf-Rayet stars might actually end its life with a GRB. And given that WR-104 is part of a binary system, its interactions with its companion may complicate or even reduce the chances of such a burst occurring. Fourth, the timescale is incredibly uncertain. WR-104 is in the final stages of its life, but in stellar terms, final could mean tomorrow, or hundreds of thousands of years from now. Human civilization is just a tiny blip on cosmic time, so the odds that WR-104's death will even coincide with our existence are vanishingly small. It's like standing near a firework that may go off at some point in the next 200,000 years. It's a theoretical risk, but not a practical one. Finally, astronomers themselves, who study WR-104 closely, are quick to reassure the public. Yes, the star is fascinating. Yes, it could theoretically produce a GRB. But in the hierarchy of cosmic threats to Earth, WR-104 doesn't even make the shortlist. Asteroids, climate change, and other nearer-term challenges are far more pressing. The Pinwheel Star is a mystery to unravel, not a reason to lose sleep. And perhaps this is where perspective matters most. The very fact that we can observe WR-104, study its dust plume, debate its alignment, and imagine its future tells us something profound about how far human knowledge has come. A century ago, the idea of detecting distant stars' life cycles would have seemed impossible. Today, we can not only watch them, but also imagine their endings and prepare models of their explosions. That knowledge itself is a comfort, because it means we are watching the cosmos with ever-growing clarity. So while the image of WR-104 as a cosmic gun pointed at Earth makes for dramatic headlines and stirring conversation, the reality is much calmer. The Pinwheel Star is unlikely to ever harm us. Instead, it offers us a chance to marvel at the universe, to study one of the most unusual stellar systems known, and to appreciate how fragile yet resilient life on Earth truly is. The next time you see WR-104 mentioned in a news article or video with doomsday undertones, remember this: the odds of danger are so small they're almost non-existent. Instead of fear, let WR-104 inspire awe at the scale of the universe and gratitude that we get to witness such beauty from the safety of our little corner of the galaxy. When it comes to the Pinwheel Star, one of the most fascinating, and sometimes frustrating, aspects of studying it is that astronomers themselves don't fully agree on whether its rotational axis is really pointed at Earth. This ongoing scientific debate is part of what keeps WR-104 at the center of both astrophysical research and public imagination. The controversy began in the late 1990s, when Peter Tuthill and his team at the Keck Observatory captured the first detailed images of the star's spiral dust plume using an interferometer. Those images were extraordinary, unlike anything ever seen before. They revealed a nearly perfect pinwheel pattern, spiraling outward from a central point like a cosmic seashell. But it wasn't just the beauty of the pattern that caught attention. It was the orientation. From our vantage point, the spiral appeared face-on, almost as if we were staring directly into the center of the whirlpool. That led to an unsettling implication. Maybe we were also looking directly down the rotational axis of WR-104, which would be the same direction a future gamma-ray burst might travel. Naturally, this sparked speculation and concern. But other astronomers quickly raised an important point. Appearances can be deceptive, especially when it comes to geometry on a cosmic scale. Just because the spiral looks face-on doesn't necessarily mean the star's axis is perfectly aligned with us. The dust plume traces the orbital motion of the binary system, but interpreting the exact tilt of the star's axis from that is far more complicated. Over the years, follow-up studies have tried to pin down the orientation more precisely. Some suggest that WR-104's axis may indeed be closely aligned with Earth's line of sight, perhaps within just a few degrees. Others argue that there's enough uncertainty in the data to conclude that the alignment could be off by a safe margin. Even a tilt of 10 or 20 degrees would be more than enough to steer any gamma-ray burst harmlessly past us. The debate highlights the difficulty of measuring stellar orientation. From 8,000 light-years away, astronomers are essentially trying to reconstruct a three-dimensional structure based on limited two-dimensional observations. Add in the complexities of the binary system, the interplay of winds, the dust production, the orbital motion, and you get a puzzle that's anything but straightforward. It's a bit like trying to guess the direction a spinning top is pointing by looking at the swirl of smoke it leaves behind. Another layer of the debate centers on whether WR-104 would even be capable of producing a gamma-ray burst at all. While it has the hallmarks of a GRB progenitor, a massive Wolf-Rayet star nearing the end of its life, the fact that it's part of a binary system complicates things. Interactions with its companion could alter its rotation, its mass loss, and even the way it collapses. Some models suggest this might prevent it from producing a GRB altogether, making the alignment question irrelevant. Others say the binary interaction could actually make a GRB more likely. What's important to note is that this isn't a debate driven by fear, it's a scientific dialogue aimed at understanding stellar physics more deeply. The Pinwheel Star offers a unique laboratory for testing theories about massive stars, their winds, their dust production, and their explosive deaths. Whether or not Earth happens to lie in the line of fire is almost incidental compared to the astrophysical insights WR-104 provides. That said, the uncertainty has helped fuel its reputation as a doomsday star. The lack of consensus gives room for speculation, and speculation often spreads faster than cautious scientific reassurance. Astronomers can say the odds are low all they want, but as long as the orientation remains unresolved, WR-104 will continue to inspire headlines, YouTube videos, and debates in both academic journals and online forums. In truth, this debate is a reminder of how much we still don't know about the universe. Even with some of the most powerful telescopes on Earth, the question of WR-104's alignment remains open. And that's the beauty of science. It's not about having all the answers, but about refining our understanding with every observation, every model, and every spirited discussion. So, while scientists may not fully agree on whether WR-104's axis is aimed at Earth, what they do agree on is that the star is an extraordinary object worthy of study. The debate itself is part of the discovery process, pushing our knowledge of stellar evolution forward one observation at a time. When it comes to the Pinwheel Star, one of the biggest reasons scientists are still debating its alignment is simply because observing and measuring something so distant is incredibly difficult. At nearly 8,000 light-years away, WR-104 lies buried deep in the crowded heart of the Milky Way, in the direction of the Sagittarius constellation. This region of space is filled with gas, dust, and countless other stars, all of which complicate astronomers' efforts to get a clear, precise picture of the system. The first challenge is distance itself. Light takes 8,000 years to travel from WR-104 to Earth, which means every image we capture today shows the star as it looked when early human civilizations were just beginning to take shape. We can't zoom in or walk around the star to get a better perspective. All we have are faint beams of light that have journeyed across thousands of years and been distorted, scattered, and absorbed along the way. Then there's the problem of dust obscuration. WR-104 produces enormous amounts of dust due to the collision of stellar winds from the Wolf-Rayet star and its companion. This dust scatters visible light, making the system extremely difficult to observe in ordinary optical wavelengths. Much of what we know about WR-104 comes from infrared observations, which can penetrate the dust and reveal the stunning pinwheel pattern. But while infrared is excellent for showing us the structure of the spiral, it doesn't always give us precise measurements of angles, rotations, or orientations at the stellar level. Another challenge comes from the binary nature of the system. WR-104 isn't a single star, it's a Wolf-Rayet star paired with a massive blue companion. The two orbit each other closely, interacting in complex ways that influence the dust spiral. The motion of the stars and the shape of the spiral give astronomers some clues about orientation, but it's a puzzle with many moving parts. Imagine trying to determine the angle of a spinning top while it's being buffeted by winds and shedding sparks in every direction. That's roughly what scientists are up against. Even when astronomers use interferometry, combining light from multiple telescopes to increase resolution, the images still leave room for interpretation. The pinwheel looks face-on, but is it perfectly aligned with Earth, or is it tilted by several degrees? With current technology, the difference between a few degrees of tilt is almost impossible to pin down with certainty. And when it comes to gamma-ray bursts, those few degrees make all the difference between devastation and safety. On top of this, the stellar interior dynamics are hidden from view. To know whether WR-104 could produce a gamma-ray burst, scientists need to understand how fast it's spinning, how much angular momentum it retains, and how its core will collapse when the time comes. None of these factors can be directly observed. Instead, astronomers rely on computer models, indirect measurements, and comparisons with other stars. Each piece of data comes with uncertainties that multiply when combined. Finally, the broader environment of the Milky Way adds noise to the picture. Observing a faint, dusty binary system against the crowded background of the galactic center is like trying to track a firefly in front of a lit-up city skyline. Separating WR-104's signals from all the other stars, gas clouds, and radiation sources in Sagittarius is an observational feat in itself. All of these challenges explain why scientists are cautious about making definitive statements regarding WR-104's orientation or fate. It's not that they don't want to give answers, it's that the universe isn't making it easy. Every observation is a triumph of ingenuity, pushing the limits of telescopes, detectors, and analytical techniques. But for now, WR-104 keeps its deepest secrets closely guarded. In many ways, the difficulties of studying WR-104 are also opportunities. Each obstacle pushes astronomers to develop new tools, like more sensitive infrared detectors or advanced interferometry techniques. Future observatories, such as the James Webb Space Telescope or next-generation ground-based telescopes with mirrors 30 meters across, may eventually give us a sharper view of the Pinwheel Star, helping to resolve some of the lingering uncertainties. Until then, WR-104 remains both a challenge and an inspiration. The very difficulty of studying it reminds us how vast and complex the universe is, and how much more we still have to learn. Much of what makes the Pinwheel Star so visually and scientifically remarkable comes from looking at it beyond the visible spectrum, through the lens of infrared astronomy. While visible light telescopes capture only a portion of the electromagnetic radiation the universe produces, infrared allows astronomers to peer through the thick dust surrounding WR-104 and reveal its extraordinary structure in stunning detail. Without infrared observations, the star's famous spiral dust plume would be almost entirely invisible to us, hidden behind clouds of gas and cosmic debris. The dust surrounding WR-104 is not merely decorative, it's a byproduct of the violent interaction between the Wolf-Rayet star and its massive blue companion. Both stars produce intense stellar winds, streams of charged particles moving at thousands of kilometers per second. When these winds collide, they compress and cool in localized regions, allowing carbon and other elements to condense into tiny dust grains. These dust grains absorb the star's intense ultraviolet and visible radiation, heat up, and then re-radiate the energy at longer infrared wavelengths. This process creates the iconic pinwheel spiral that makes WR-104 one of the most visually striking stellar systems ever imaged. Infrared telescopes, which detect radiation in wavelengths far longer than visible light, can capture the warm glow of the dust as it spirals outward. Observations at these wavelengths have revealed the spiral structure extending for tens of astronomical units, enough to dwarf the size of our entire solar system. Each loop of the spiral traces a single orbit of the binary system, and the full pattern rotates over time as the stars complete their cosmic dance. The first high-resolution infrared images of WR-104 were captured using interferometry, which combines light from multiple telescopes to achieve the resolution of a much larger instrument. Using this technique, astronomers were able to resolve the spiral for the first time, providing concrete visual evidence of the binary system's orbital motion and the pattern of dust creation. These images were groundbreaking, not only because they revealed the structure itself, but because they allowed scientists to measure the rate at which the spiral rotates and the speed at which the dust travels outward. Infrared observations also provide a wealth of quantitative information. By analyzing the brightness of the dust at different wavelengths, astronomers can estimate its temperature, composition, and mass. For WR-104, the dust is found to be relatively warm, several hundred degrees Celsius, and primarily composed of carbon-rich grains. Understanding these properties helps researchers model how massive stars like WR-104 lose mass, form dust, and influence the surrounding interstellar medium. Moreover, infrared imaging is essential for understanding the broader implications of WR-104 as a potential gamma-ray burst progenitor. Because the dust can obscure visible light, infrared allows astronomers to trace the system's geometry and orientation without interference. Observing the spiral face-on provides hints about the star's rotational axis, which is crucial when assessing alignment concerns with Earth. The aesthetic impact of infrared observations cannot be overstated. The spiral looks almost like a celestial pinwheel toy or a miniature galaxy, with glowing arms elegantly curving outward. Each loop is a timestamp of the star's orbital motion, a frozen imprint of cosmic wind and dust shaped over years. The images are both scientifically valuable and profoundly beautiful, reminding us that some of the universe's most fascinating phenomena are invisible to the naked eye. It's worth noting that these infrared techniques are not unique to WR-104. They have been applied to other Wolf-Rayet stars and dusty binaries. However, WR-104 remains unique because of the clarity and scale of its spiral, making it the archetype of a pinwheel nebula. Its beauty, revealed through infrared light, is a direct product of the violent, high-energy interactions that make Wolf-Rayet stars so extreme. In essence, infrared observations have transformed WR-104 from a faint, obscure star into one of the most iconic astronomical objects known. Without the ability to see beyond visible light, the star's structure, dynamics, and even its potential alignment with Earth would remain almost entirely speculative. Infrared imaging allows us to witness the Pinwheel Star in all its glory, capturing both the elegance of the spiral and the immense energy driving its creation. One of the most enduring and iconic aspects of the Pinwheel Star is undoubtedly its cosmic pinwheel image, a breathtaking visual that has captivated both astronomers and the public alike. The spiral dust plume surrounding WR-104 is so striking that when it was first imaged, it instantly became one of the most famous examples of stellar artistry in the universe. These images do more than please the eye. They tell a story about the star's physical processes, its binary dance, and the interplay of forces shaping matter on a cosmic scale. The first high-resolution images were obtained in the late 1990s using infrared interferometry, a technique that combines the light collected by multiple telescopes to simulate the resolution of a much larger instrument. Observing in the infrared allowed scientists to penetrate the dense clouds of dust that obscure WR-104 in visible light, revealing the full elegance of its spiral. The resulting images looked almost surreal, a glowing, luminous swirl of dust, coiling outward like the arms of a miniature galaxy or a giant celestial pinwheel toy. Each curve and loop traced the orbital motion of the binary stars at the heart of the system, creating a perfect logarithmic spiral that is as mathematically beautiful as it is visually stunning. The structure of the spiral is fascinating. Each full turn corresponds to one orbit of the binary system, which takes approximately 8 months to complete. As the stars orbit each other, their colliding winds generate dust that is continuously pushed outward, forming the spiral pattern we see. The spiral arms are essentially a timestamp of the binary's motion, a living record of their dance frozen in glowing dust. Over time, the pattern slowly expands, but the overall symmetry remains, giving the impression of a perfect cosmic pinwheel spinning in the vast emptiness of space. These images are more than just beautiful, they are scientifically informative. By studying the spacing and curvature of the spiral, astronomers can determine the velocity of the dust as it leaves the system, the rate at which WR-104 loses mass, and even estimate the dynamics of the binary stars themselves. The cosmic pinwheel is essentially a natural laboratory, providing a rare opportunity to observe the interactions of massive stars in exquisite detail. The visual impact of the images has also made WR-104 an object of fascination in popular culture. The spiral has been reproduced in countless articles, documentaries, and even art, often accompanied by the dramatic speculation about its potential as a doomsday star. The contrast between the star's delicate, almost playful appearance and its violent, high-energy nature captures the imagination like few other celestial objects. It's a star that is both beautiful and potentially dangerous, a duality that makes it endlessly compelling. Infrared images of WR-104 also serve as a reminder of the power of technology in modern astronomy. The details visible in the pinwheel, curving arcs, tightly wound spirals, and glowing dust lanes, would have been impossible to detect with the telescopes of even a few decades earlier. The combination of interferometry and infrared imaging not only revealed the spiral but allowed astronomers to measure its expansion rate, the speed of stellar winds, and the periodicity of the binary orbit. In essence, the cosmic pinwheel image transformed WR-104 from a distant point of light into a fully realized system whose behavior we can observe, model, and understand. The resemblance to a pinwheel toy is more than just poetic. In both the toy and the star, we see a central hub producing a repeating, outward-moving pattern. In the case of WR-104, the hub is the binary star system, and the arms are composed of dust blown outward by powerful winds. The visual analogy helps us grasp the motion and symmetry of the system, something that might otherwise be abstract and difficult to conceptualize. And unlike a toy, this cosmic pinwheel operates on a scale that is almost unimaginable. The spirals stretch over tens of astronomical units, dwarfing our entire solar system, and the energy driving them is millions of times greater than anything humans could produce. Finally, the cosmic pinwheel image has become a symbol of the Pinwheel Star's dual nature. From afar, it appears serene and graceful, a hypnotic swirl suspended in space. But underlying that beauty is a violent, high-energy system hurtling toward its eventual demise. It's a visual metaphor for the balance of beauty and danger in the cosmos, creation and destruction occurring simultaneously, captured in a moment of stunning symmetry. One of the most mesmerizing aspects of the Pinwheel Star's dust spiral is that it's not static. It's a living, dynamic structure that rotates in sync with the orbit of the binary stars at its heart. The spiral pattern, which we admire in infrared images, is a direct consequence of the orbital dance between WR-104 and its massive blue companion. As the two stars orbit each other, their powerful stellar winds collide, producing dust that is pushed outward and twisted into the characteristic pinwheel shape. Over time, this process creates a continuous, rotating spiral that evolves as the system rotates. The binary stars at the center of WR-104 orbit each other roughly every 8 months. Each orbit generates a new loop of dust in the spiral, much like the arms of a clock marking the passage of time. As the stars revolve, the spiraling wind patterns carry the newly formed dust outward, creating a long, luminous arm that extends across space. Each loop is essentially a snapshot of one orbital period, a cosmic timestamp frozen in glowing dust. Observing these loops allows astronomers to measure the speed at which the dust is expelled, the mass loss rate of the Wolf-Rayet star, and even the relative orientation of the two stars. The rotation of the spiral is not only visually striking but also scientifically significant. By monitoring how the spiral arms move over months and years, astronomers can calculate the orbital period of the binary system with impressive precision. The consistency of the spiral also confirms that the dust production is steady and linked directly to the colliding winds of the two stars. Any variations in the spiral's shape or brightness could indicate changes in the star's wind strength or interactions, providing clues about the physical processes at work in the system. The expanding spiral arms are another fascinating feature. As the stars orbit each other and generate new loops of dust, the older loops continue to drift outward at thousands of kilometers per second. Over time, the spiral unwinds like a giant cosmic corkscrew, stretching far beyond the central stars. This outward motion not only traces the rotational period of the binary system but also offers insight into the dynamics of mass loss from Wolf-Rayet stars. It's a rare opportunity for astronomers to watch a massive star sculpt its surroundings in real time, providing a window into processes that occur over thousands of years but are measurable within human lifetimes. Interestingly, the rotating spiral also allows researchers to estimate distances and other properties of the system. By combining measurements of the angular size of the spiral with the known speed of dust expansion, astronomers can refine calculations of WR-104's distance from Earth. This makes the pinwheel spiral both a visual and quantitative tool, an elegant example of how beauty and science intersect in astronomy. The rotation also emphasizes the dynamic nature of massive stars. Unlike smaller stars like the Sun, whose visible output is relatively steady over decades or centuries, WR-104's environment is a whirlwind of activity. The stellar winds, the dust formation, and the orbital motion all interact to produce a constantly evolving pattern, demonstrating the extreme energy and complexity of Wolf-Rayet systems. From a purely aesthetic standpoint, watching the spiral rotate, even conceptually, is mesmerizing. Each orbit adds a new loop, each loop moving outward, giving the impression of a slow, majestic twirl that could continue for millennia. It's a cosmic dance frozen in space, a visual record of time, energy, and motion in a system that is simultaneously fragile and explosive. In essence, the rotation of the spiral is a physical manifestation of the binary system's orbital mechanics. It links the unseen motion of stars with the visible structure of dust, allowing astronomers to read the history of the system directly from its swirling arms. The spiral isn't just a static ornament, it's a dynamic chronicle of the Pinwheel Star's life and activity, showing how beauty and physics intertwine on a grand cosmic scale. The Pinwheel Star stands out among Wolf-Rayet stars for a very simple reason. Its spiral dust plume is visible and remarkably well-defined, something that is extraordinarily rare in these types of massive stellar systems. While Wolf-Rayet stars themselves are not unusual, they represent a brief but energetic phase in the life of massive stars. Very few display the kind of dramatic, structured dust patterns seen in WR-104. In most Wolf-Rayet systems, any dust that forms is either dispersed too quickly, obscured by surrounding material, or too faint to be resolved into a clear structure. Most Wolf-Rayet stars are shrouded in intense winds and radiation. Their outer layers are expelled at thousands of kilometers per second, creating a turbulent and often chaotic environment around the star. While these winds do produce dust in some cases, the dust tends to be diffuse, forming amorphous clouds rather than distinct shapes. WR-104 is exceptional because it is part of a tight binary system. The presence of its massive blue companion star plays a critical role in shaping the dust into a coherent spiral pattern. As the two stars orbit each other, their colliding winds compress and channel the material, producing the pinwheel effect. Without the companion star's influence, the dust would likely disperse into an unremarkable cloud. Even among Wolf-Rayet binaries, WR-104 is unusual because the spiral is visible from Earth. Observing a well-defined structure requires that the orientation of the system be favorable, essentially, that we are looking nearly face-on at the spiral. Many other Wolf-Rayet binaries with similar dust production exist, but their spirals are either edge-on or otherwise obscured, making it impossible to detect the intricate pinwheel shape. This makes WR104 a kind of Rosetta Stone for understanding dust formation and orbital dynamics in massive binary systems. Its orientation and clarity give astronomers a rare opportunity to study these processes in unprecedented detail. Another point of comparison is the rate and amount of dust formation. WR104 produces dust consistently, creating a spiral that extends outward over astronomical units. In contrast, many Wolf-Rayet stars produce dust sporadically or in limited quantities, so even if a spiral forms temporarily, it dissipates before it can be clearly observed. The combination of continuous dust production, binary dynamics, and a favorable orientation makes WR104 stand apart in the population of Wolf-Rayet stars. The visible spiral also allows astronomers to study the interaction of stellar winds in a way that is impossible with most other massive stars. By analyzing the spiral's shape, brightness, and expansion, scientists can infer wind speeds, density, and the physics governing how massive stars shed their outer layers. These insights are critical not only for understanding WR104 but also for modeling the life cycles of other Wolf-Rayet stars and predicting how they may end their lives, whether in supernovae or, potentially, gamma-ray bursts. Finally, WR104's prominence is amplified by the aesthetic and symbolic impact of the spiral. While most Wolf-Rayet stars are scientifically interesting but visually obscure, the pinwheel pattern is immediately striking and intuitive, making it a rare case where scientific data and visual splendor coincide. It has become the archetype for dusty Wolf-Rayet binaries, often referenced in both scientific literature and popular media as a classic example of stellar beauty paired with extreme astrophysical power. In short, WR104 is unusual among Wolf-Rayet stars because of a perfect storm of factors: a companion star that shapes its dust, an orientation that favors observation from Earth, and a level of dust production that allows the spiral to remain coherent and luminous. Its visible spiral makes it an extraordinary laboratory for astrophysics and a stellar spectacle unlike nearly any other in the galaxy. The Pinwheel Star's extraordinary characteristics, its spiral dust plume, extreme mass, and potential to produce a gamma-ray burst, have made it a source of fascination not just for astronomers, but for the public at large. Over the past 2 decades, WR104 has earned the nickname Doomsday Star, a label that highlights both our natural curiosity about cosmic threats and the way dramatic celestial events capture human imagination. The cultural fascination with WR104 began in earnest after the late 1990s, when high-resolution infrared images revealed its iconic spiral. The stunning pinwheel pattern immediately drew attention, but it was the accompanying discussion of gamma-ray bursts that cemented its reputation as a potential cosmic menace. Media outlets, science blogs, and documentaries seized upon the idea that this relatively nearby star could, in theory, send a concentrated beam of gamma radiation directly toward Earth. Headlines were sensational. Phrases like Doomsday Star, Cosmic Death Beam, and Apocalyptic Star in our backyard became common. While these descriptions were often exaggerated, they tapped into a primal human fascination with existential risk and the unknown. The idea of WR104 as a doomsday star has a particular appeal because it combines beauty and danger. Its spiral dust plume looks elegant, almost delicate, yet it conceals a star system capable of releasing unimaginable energy in the form of a supernova or gamma-ray burst. This contrast between aesthetic serenity and potential destruction resonates deeply with our imagination. It's a cosmic paradox, an object that is visually mesmerizing yet theoretically lethal, embodying the duality of creation and annihilation in the universe. Science fiction and popular culture have also latched onto WR104's mystique. While it has yet to become a household name like Betelgeuse or Sirius, the star often appears in discussions of astronomical hazards, end-of-the-world scenarios, and cosmic phenomena in documentaries and online media. Its dramatic story is easy to communicate: a spinning star thousands of light-years away, shedding dust in a perfect spiral, with a possible death ray aimed at our planet. The narrative fits neatly into human storytelling traditions: heroes, villains, and the looming threat of unseen forces. Interestingly, WR104's notoriety as a doomsday star has sparked serious scientific discourse alongside popular fascination. The sensational framing has helped draw attention to the study of gamma-ray bursts, Wolf-Rayet stars, and the broader implications of massive stellar deaths. Public interest has, in a way, amplified funding, research attention, and educational opportunities surrounding these extreme astrophysical events. The star has become both a cautionary tale and a teaching tool, illustrating the immense scales, energies, and timescales that govern the cosmos. Despite the dramatic moniker, the scientific community has been careful to temper the panic. Researchers emphasize that the likelihood of WR-104 ever harming Earth is extraordinarily low. Still, the story of the Pinwheel Star as a doomsday object persists, capturing imaginations with its combination of visual splendor, scientific intrigue, and potential threat. It's a reminder of how the universe can be both beautiful and frightening, and how a single object 8,000 light-years away can spark wonder and speculation here on Earth. The fascination also taps into something deeply human, our curiosity about the unknown, and our instinct to seek meaning or narrative in the cosmos. WR-104 embodies that tension perfectly. On one hand, it is a distant, impersonal collection of gases, dust, and radiation, operating according to physical laws indifferent to human life. On the other hand, it occupies our imagination as a tangible threat, a celestial entity that could, in a worst-case scenario, impact our planet. This duality, science versus narrative, is what gives WR-104 its lasting cultural appeal. Moreover, the star's doomsday narrative often serves as an entry point for broader discussions about astrophysics, stellar evolution, and cosmic hazards. WR-104 is a gateway for people to learn about the life cycles of massive stars, the mechanics of gamma-ray bursts, and the role of binary systems in shaping stellar behavior. In that sense, its cultural fascination is not just about fear, it's also about education, inspiration, and the human desire to connect with the cosmos. In short, WR-104 has captured public imagination because it combines awe-inspiring beauty, extreme physical processes, and a hypothetical existential threat into one coherent story. Its spiral dust plume is elegant, its energy output staggering, and its potential danger dramatic enough to fuel speculation for years. It's a star that exists at the intersection of science, imagination, and human storytelling. A perfect example of how the universe can both mesmerize and unsettle us at the same time. The Pinwheel Star is not just a captivating cosmic object for its visual beauty or speculative doomsday potential. It is also incredibly valuable scientifically, offering astronomers a rare window into some of the most extreme processes in stellar evolution and the origins of gamma-ray bursts. Its unique combination of properties, a Wolf-Rayet star in a close binary system, producing a well-defined spiral dust plume, and nearing the end of its life, makes WR-104 an unparalleled laboratory for studying high-energy astrophysics. One of the most significant areas of research is stellar evolution, particularly the late stages of massive stars. Wolf-Rayet stars represent a brief but critical phase in the life cycle of stars much more massive than the Sun. During this stage, the star sheds its outer layers at extraordinary rates, exposing its hot, dense core. Studying WR-104 allows astronomers to observe how massive stars lose mass through powerful winds and how these winds interact with their environment. Because WR-104 is part of a binary system, it provides an even richer context. The companion star's presence affects the structure, velocity, and composition of the outflowing material, giving scientists an opportunity to model how binaries influence stellar evolution. The dust spiral around WR-104 offers a direct view of mass loss processes in action. Most Wolf-Rayet stars produce winds that are difficult to study because they're either too diffuse or obscured. WR-104, by contrast, creates a coherent spiral of dust that is observable in infrared light. Each loop of the spiral corresponds to a single orbit of the binary stars, acting as a timestamp of their interactions. By studying the shape, expansion rate, and brightness of these loops, astronomers can calculate the speed of stellar winds, the rate of mass loss, and even the temperature and composition of the expelled material. These measurements feed into models that help us understand how massive stars evolve, how they shed angular momentum, and how they prepare for their final explosive deaths. Beyond stellar evolution, WR-104 is critically important for understanding gamma-ray burst progenitors. Long-duration GRBs, the kind associated with massive stars, require very specific conditions. A massive, rapidly rotating star that collapses into a black hole, launching narrow jets of energy along its rotational axis. WR-104 exhibits many of the characteristics of such a progenitor, making it a prime target for studying the conditions that might lead to these catastrophic explosions. By monitoring its rotation, mass, and binary interactions, astronomers can refine models that predict which stars might produce GRBs and under what circumstances. WR-104 acts as a nearby example of a class of stars that are otherwise mostly observed at cosmological distances when they explode, allowing for detailed, long-term studies that would be impossible with distant GRB sources. Furthermore, WR-104 provides a unique opportunity to test astrophysical models in real time. Its dust spiral rotates predictably, with each orbital loop representing a controlled experiment in stellar wind interaction. Observations over months and years allow astronomers to compare theoretical predictions with actual measurements, refining their understanding of binary dynamics, wind collisions, and dust formation. This kind of empirical data is rare for massive stars at this stage of life, making WR-104 an invaluable benchmark for the field. The scientific value of WR-104 also extends to broader cosmic questions. For example, understanding how Wolf-Rayet stars lose mass and evolve helps astronomers predict the chemical enrichment of galaxies, as these stars eject heavy elements like carbon and oxygen into interstellar space. This, in turn, informs models of star formation, planet formation, and even the evolution of life-friendly environments in galaxies. Observing WR-104 is like watching a miniature cosmic ecosystem in motion. We see how massive stars shape their surroundings and prepare the ingredients for future generations of stars and planets. Finally, WR-104 has value simply because of its rarity. While Wolf-Rayet stars are relatively uncommon, those with visible dust spirals and favorable orientations for study are extraordinarily rare. WR-104 is essentially a Rosetta Stone for understanding the interactions between massive binaries, stellar winds, dust production, and the mechanisms that can lead to gamma-ray bursts. Its combination of observability, proximity, on a cosmic scale, and extreme physical conditions makes it one of the most studied Wolf-Rayet stars in the galaxy. In short, WR-104 is much more than a pretty spiral or a hypothetical hazard. It is a scientific goldmine, helping astronomers unlock the mysteries of stellar life cycles, binary dynamics, high-energy astrophysics, and gamma-ray burst origins. Its study advances our understanding of some of the most powerful and dramatic processes in the universe, offering insights that can be applied across astrophysics, from the tiniest dust grains spiraling outward to the most energetic explosions across billions of light-years. One of the most compelling aspects of the Pinwheel Star is the striking duality between its serene beauty and its underlying potential for destruction. From an observational standpoint, WR-104 is breathtaking. A luminous spiral dust plume elegantly winding outward from a brilliant binary core, resembling a cosmic pinwheel spinning silently in the depths of space. The symmetry and precision of the spiral evoke a sense of calm, order, and aesthetic perfection, as though the universe itself had paused to craft a work of art. Yet beneath this mesmerizing appearance lies an immense reservoir of cosmic energy and potential devastation. WR-104 is a Wolf-Rayet star, a massive, highly unstable, an extremely hot star shedding its outer layers at incredible speeds. The very processes that create the graceful dust spiral, the colliding stellar winds, the high rotation, the binary interaction, also mark the system as a candidate for a cataclysmic end. When the star finally exhausts its nuclear fuel, it may explode as a supernova, or even unleash a long-duration gamma-ray burst, GRB. The contrast between the calm elegance of the spiral and the violent fate of the stars themselves is stark. The same system that produces a delicate, ordered structure also harbors the potential to release energies capable of sterilizing planets across thousands of light-years. This duality has made WR-104 an object of both fascination and unease. Astronomers marvel at its dust plume as a laboratory of stellar physics, tracing the dynamics of binary orbits, wind collisions, and dust formation in exquisite detail. Yet, the very same observations that reveal the spiral also inform calculations about GRB alignment, energy output, and potential effects on Earth. Hypothetical consequences that, while extraordinarily unlikely, are undeniably powerful. The star embodies the paradox of the cosmos. Phenomena that are visually stunning can simultaneously represent unimaginable power and danger. The contrast is further emphasized when we consider scale and energy. The spiral extends tens of astronomical units, dwarfing our solar system, yet it is composed of matter expelled at speeds of thousands of kilometers per second. The luminosity of the system is millions of times that of our Sun, radiating not only visible light but also intense ultraviolet radiation. A gamma-ray burst from this system would concentrate that energy into a narrow beam capable of traversing the 8,000 light-years to Earth with devastating potential. In other words, WR104 is both delicate and extreme, a celestial paradox where beauty and lethality coexist. Culturally, this duality has also captured imagination. WR104 is often described as a doomsday star, yet people are equally captivated by its elegant spiral and the way it seems almost playful in its symmetry. The juxtaposition, an object that appears tranquil and orderly, yet could theoretically unleash destruction on a planetary scale, makes it a perfect metaphor for the unpredictability and power of the universe. Unlike phenomena such as black holes or distant quasars, which are abstract and difficult to visualize, WR104 allows us to see beauty and danger intertwined in a tangible, almost familiar form. From a scientific perspective, the duality is not just poetic, it is functional. The very mechanisms that give rise to the aesthetic spiral are the same that govern the star's extreme energy output and potential for a GRB. By studying the dust plume and its structure, astronomers gain insight into the same processes that could, in theory, produce a gamma-ray burst. The beauty of the spiral is essentially a map of the physics that drives the star's ultimate fate, making WR104 a rare object where aesthetics and high-energy astrophysics are inseparable. Ultimately, WR104 is a cosmic lesson in contrasts. Its visual serenity draws observers in, offering wonder and awe, while its potential destructive power reminds us of the immense scales and energies at play in the universe. It is a stellar system that teaches humility. The universe can craft structures of exquisite beauty while simultaneously harboring forces capable of profound transformation, or even annihilation, across vast distances. The Pinwheel Star embodies both the artistry and the danger inherent in cosmic evolution, making it one of the most compelling objects in modern astronomy. The Pinwheel Star serves as an extraordinary natural laboratory for studying some of the most extreme astrophysical processes in the universe, and it has already taught astronomers a tremendous amount about stellar winds, dust formation, and binary interactions. Each loop of its spiral dust plume is more than just a visual marvel, it's a record of complex physics, revealing the interplay of forces that govern massive stars and their environments. One of the first lessons WR104 offers is about stellar winds. Wolf-Rayet stars are among the most extreme in terms of mass loss. They blow off material from their outer layers at speeds of thousands of kilometers per second, creating supersonic outflows that carry enormous amounts of energy into space. In isolation, these winds are chaotic and difficult to study. But in WR104, the interaction between the Wolf-Rayet star and its massive blue companion channels these winds into a highly organized pattern. The spiral dust plume shows how colliding winds from massive stars can compress gas, generate shocks, and shape the surrounding environment in surprisingly coherent structures. By analyzing the spiral's geometry, astronomers can measure wind velocities, densities, and the dynamics of collision zones, providing a direct window into processes that are otherwise invisible. The system also sheds light on dust formation in hostile environments. Wolf-Rayet stars are incredibly hot, with surface temperatures exceeding 40,000 degrees Celsius, conditions under which dust should be easily destroyed. Yet WR104 proves that dust can form even in these extreme settings, given the right circumstances. The collision of the Wolf-Rayet star's wind with that of its companion creates regions of localized compression and cooling, allowing carbon-rich particles to condense into dust grains. The spiral itself is essentially a cosmic conveyor belt of freshly minted dust, expanding outward and glowing in infrared light. Studying this process teaches astronomers about the efficiency of dust formation in extreme stellar environments and provides clues about how massive stars contribute to the chemical enrichment of galaxies. Another key insight comes from binary interactions. WR104 demonstrates how companion stars influence the evolution and behavior of massive stars. The spiral would not exist without the gravitational and wind interactions from the secondary star. Its orbit shapes the flow of material, stabilizes the spiral, and affects the mass loss patterns of the Wolf-Rayet primary. Understanding these binary effects is crucial because a significant fraction of massive stars exist in binaries, and their interactions often determine whether they will end as supernovae, neutron stars, or black holes. WR104 provides a rare opportunity to see these effects in action, allowing astronomers to model mass transfer, angular momentum loss, and wind-wind collisions with real observational data rather than theoretical extrapolation. Observing WR104 over time also teaches us about the dynamics of dust spirals. Each orbital period adds a new loop to the pinwheel, and older loops expand outward as newer ones form. By monitoring these spirals, astronomers can track how the system evolves, measure expansion rates, and infer the forces shaping the dust. This continuous living record is invaluable for refining models of stellar winds, mass loss rates, and the mechanisms that allow dust to survive in extreme conditions. Furthermore, WR104 informs research into the progenitors of gamma-ray bursts. Its high mass, rapid rotation, and binary interactions mirror the conditions that might produce long-duration GRBs when the Wolf-Rayet star eventually collapses. By studying the orientation of the spiral, the dynamics of the binary, and the mass loss history, scientists can better predict which systems are likely to generate GRBs, how angular momentum is retained, and how the surrounding environment might affect the propagation of such an energetic explosion. In this sense, WR104 is a rare example of a star system where we can observe both the physical precursors and the processes leading up to some of the most violent events in the universe. WR104 also highlights the interconnectedness of stellar phenomena. Stellar winds influence dust formation. Dust can be shaped by binary dynamics. Mass loss affects future supernova potential, and all of these factors together can determine whether a GRB occurs. By offering a system where all these variables are measurable and observable, the Pinwheel Star acts as a natural experiment in extreme astrophysics, allowing scientists to test theories that would otherwise remain purely theoretical. Finally, the study of WR104 has broader implications for understanding the cosmic ecosystem. The dust it produces will eventually disperse into the interstellar medium, seeding future generations of stars and planets with heavy elements like carbon. The energy injected by its winds influences nearby molecular clouds, potentially triggering star formation or sculpting galactic structures. Observing WR104 gives us a front-row seat to these processes, connecting the life cycle of a single binary star system to the broader evolution of galaxies and the universe itself. In short, WR104 teaches us that even in the most extreme, high-energy environments, the universe operates with an underlying order. Its spiral dust plume is not just beautiful, it is a map of physics in action, revealing how massive stars interact, how dust forms and survives, and how binary companions shape stellar destiny. Each loop, each glimmer of infrared light, carries information about processes that govern the life and death of the most massive stars in the galaxy, providing insights that are impossible to obtain from solitary or more chaotic systems. The future of the Pinwheel Star is both inevitable and fascinating. Eventually, WR104 will reach the end of its life and explode. Like all Wolf-Rayet stars, it is in the final stages of stellar evolution, burning through the last reserves of nuclear fuel in its core. This process has been ongoing for millions of years, but in stellar terms, WR104 is now a ticking clock, slowly but steadily approaching its ultimate fate. Despite the dramatic discussions of potential gamma-ray bursts, it's important to keep perspective. Eventually in this context could mean hundreds of thousands of years, or even longer. Wolf-Rayet stars are short-lived compared to stars like our Sun, but their exact remaining lifetime is difficult to pin down. Estimates for WR104's time left range from a few tens of thousands to a few 100,000 years, a blink of an eye in cosmic terms but far beyond a human lifetime. From Earth's perspective, this means that while its explosion is certain in the long run, it is highly unlikely to occur anytime soon. When WR104 exhausts its nuclear fuel, its core will collapse under gravity, triggering a supernova. This is the natural endpoint for massive stars, an enormous explosion that can briefly outshine entire galaxies. The material from the star's outer layers will be ejected at tremendous speeds, enriching the surrounding interstellar medium with heavy elements like carbon, oxygen, and nitrogen. This process is fundamental to the cosmic cycle of matter, providing the building blocks for new stars, planets, and potentially even life. In that sense, WR104's death will be a creative event as much as a destructive one, contributing to the ongoing evolution of the galaxy. For WR104, the possibility exists that this supernova could produce a long-duration gamma-ray burst if certain conditions are met. Specifically, if the star's rotation is rapid and the collapse is aligned along its rotational axis. However, even if a GRB occurs, it would be a brief, highly focused event. The The vast distance of 8,000 light-years acts as a buffer, and astronomers continue to debate whether the star's orientation makes Earth vulnerable at all. Most models suggest that even with an explosion, the chances of catastrophic effects for our planet remain extraordinarily low. The extended timeline also allows astronomers to continue observing WR-104 in unprecedented detail. Unlike supernovae that occur unpredictably and explode in a matter of days, WR-104 provides a long-term laboratory. Researchers can monitor changes in the dust spiral, track the binary orbit, measure wind speeds, and refine models of stellar evolution and GRB potential over decades. Each year of observation adds valuable information, allowing scientists to prepare for, or at least understand, the mechanisms that will eventually culminate in its explosive end. In many ways, the prolonged life remaining for WR-104 emphasizes the scale of cosmic time. While humans often think of events in terms of years or centuries, stars like WR-104 operate on astronomical timescales, where hundreds of thousands of years can pass between critical stages. The star's future explosion is inevitable, but it serves as a reminder that the universe evolves slowly, often in ways that are imperceptible within a single human lifetime. This long timeline also underscores the star's dual nature as both a ticking clock and a cosmic work of art. While it is gradually heading toward an explosive end, it continues to produce a beautiful, dynamic spiral that rotates and expands, illuminating the physics of massive binaries for astronomers. The interplay of its ongoing dust formation, stellar winds, and orbital motion is essentially a preview of the processes that will eventually culminate in a supernova or GRB. Finally, WR-104's eventual explosion is a demonstration of cosmic cycles. Like all stars, it is part of a larger ecosystem. It was born from earlier generations of stars, and its death will seed the galaxy with elements for future generations. The Pinwheel Star reminds us that creation and destruction are intertwined on a universal scale. Even in the face of its immense power, the star contributes to the long-term evolution of the galaxy, leaving behind a legacy of both beauty and matter. In short, the future of WR-104 is certain yet distant. It will explode, enriching the cosmos and potentially producing spectacular high-energy phenomena. But these events are measured in hundreds of thousands of years, giving humanity ample time to observe, study, and appreciate the system in its current form. The Pinwheel Star is a living example of the slow, majestic rhythms of the universe, a star in motion, a spiral in time, and a future supernova waiting on a cosmic schedule far beyond our own. Despite all the dramatic headlines and speculative doomsday scenarios, it's important to step back and gain a rational perspective on the actual danger WR-104 poses to Earth. While the star has the potential to produce a supernova, and perhaps, under very specific conditions, a long-duration gamma-ray burst, the likelihood of any catastrophic effects here on our planet is extremely low. First, consider the distance. WR-104 is approximately 8,000 light-years away, which is staggeringly far in human terms. Even a supernova or GRB occurring at that distance would have its energy spread over an enormous area, reducing the potential impact on Earth. For comparison, supernovae that have occurred within a few hundred light-years of our solar system have left no detectable signs of major harm, and gamma-ray bursts are far more directional, meaning only a narrow beam of radiation would carry the destructive energy. If the beam isn't precisely aligned with Earth, which, as scientists continue to study, is uncertain, there is effectively no danger. Second, the probability of alignment is exceedingly low. Even if WR-104 were capable of producing a long gamma-ray burst, the jet would be narrow, covering only a tiny fraction of the sky. Imagine the star firing a cosmic laser thousands of light-years away. The odds that Earth happens to lie in the path of that beam are minuscule. Astronomers estimate that the probability of any life-threatening event from WR-104 is so small that it doesn't warrant alarm. In other words, while the possibility is scientifically interesting, it is not practically threatening. Third, WR-104 is slowly evolving on a timescale far longer than human lifetimes. Even in the unlikely event that it explodes sooner rather than later, the energy from the supernova or gamma-ray burst would take thousands of years to reach us, giving astronomers ample time to observe, analyze, and model the effects. The universe operates on scales that dwarf human experience, and stars like WR-104 remind us of the vastness of cosmic time. Our place in that timeline is infinitesimal, and the immediate risk is effectively zero. Moreover, astronomical observations continue to refine our understanding. Researchers study the orientation, rotation, and stellar winds of WR104 in order to determine the true likelihood of a harmful alignment. While there is ongoing scientific debate, the prevailing consensus is reassuring. Even if the rotational axis were roughly aligned toward Earth, the combination of distance, jet dispersion, and probabilistic orientation makes a catastrophic outcome extraordinarily unlikely. It's also worth noting that Earth has survived nearby stellar explosions in the past without experiencing mass extinction from gamma-ray bursts. The galaxy is filled with massive stars and potential GRB progenitors, yet life persists. WR104 is just one of thousands of massive stars in our region of the Milky Way, and humanity has endured billions of years of cosmic activity. Our planet is resilient, and cosmic distances provide a natural buffer. The main takeaway is that while WR104 is scientifically fascinating and hypothetically capable of extraordinary power, there is no reason to panic. Its beauty, spiral structure, and potential for high-energy events make it an invaluable object of study, not a direct threat. By observing it, we gain insights into stellar evolution, binary dynamics, and gamma-ray bursts, all without needing to fear imminent danger. In fact, the star's very distance and slow evolution allow us to enjoy and study it safely. The Pinwheel Star's dust spiral continues to rotate, its infrared glow reveals the dynamics of its winds, and its binary orbit continues to produce loops that serve as a cosmic clock. These phenomena are all occurring on timescales and distances that are entirely comfortable for Earth-based observers, making WR104 a perfect example of high-energy astrophysics without immediate hazard. In short, the perspective on danger is clear. WR104 is a potential cosmic powerhouse, yes, but it is far enough away, and the odds of a lethal alignment are so low that for all practical purposes, Earth is safe and secure. Humanity can marvel at the spiral, study the binary system, and even speculate about its explosive future, all without fear. The star's true value lies in its capacity to teach us about the universe, not to threaten us. To truly appreciate the significance of the Pinwheel Star, it helps to step back and look at the bigger cosmic picture. WR104 is remarkable in its proximity, spiral structure, and potential energy output, but it is also just one of thousands of Wolf-Rayet stars scattered throughout the Milky Way, and among countless billions across the observable universe. Putting it into context reveals both how common these stars are and how extraordinary it is to observe one in such clarity. In our own galaxy, astronomers estimate there are about 600 to 1,000 Wolf-Rayet stars, though new discoveries occasionally adjust that number. These stars are rare compared to main sequence stars like the Sun because the Wolf-Rayet phase is extremely short, typically lasting a few 100,000 years. They represent the brief, final stages of life for stars that are more than 20 to 25 times the mass of the Sun. Despite their rarity, Wolf-Rayet stars are enormously influential. Their intense winds and radiation shape the interstellar medium, trigger star formation, and seed galaxies with heavy elements such as carbon, nitrogen, and oxygen. When we expand to the cosmic scale, the numbers become staggering. The observable universe contains roughly 2 trillion galaxies, each with billions or even trillions of stars. Even if Wolf-Rayet stars account for only a tiny fraction of all stars, this translates into billions of Wolf-Rayet stars across the universe. Each one is a potential supernova candidate, and a subset may produce long-duration gamma-ray bursts under the right conditions. Massive stars with rapid rotation and certain internal compositions. Observations of distant GRBs suggest that they are rare but not exceptionally so. Astronomers detect dozens to hundreds each year across the sky, although most occur in galaxies billions of light-years away. WR104 gains its prominence in this cosmic context because it is relatively close, observable, and oriented in a way that allows detailed study. Most Wolf-Rayet stars exist too far away, are obscured by dust, or are in orientations that make their dust production invisible. WR104, with its visible spiral plume and accessible distance, serves as a local example of processes that are otherwise only inferred from distant events. By studying it, astronomers can understand GRB progenitors and stellar evolution in a way that would be impossible if relying solely on extragalactic observations. In terms of potential gamma-ray bursts, the numbers emphasize perspective. While billions of massive stars exist, the fraction that produces a long-duration GRB pointed toward Earth is extremely small. GRBs are highly directional. Even stars capable of producing them will only affect a tiny slice of space. The fact that WR104 has even been considered a candidate for a GRB does not imply imminent danger. It is simply a unique opportunity to observe a system with some of the necessary conditions for such a rare event. Additionally, the study of WR104 helps astronomers understand population statistics. By examining the frequency, mass loss rates, rotation speeds, and binary interactions of nearby Wolf-Rayet stars, scientists can extrapolate the likelihood of GRBs across the galaxy and beyond. This allows models to predict not only the occurrence of gamma-ray bursts but also the contribution of massive stars to galactic evolution, chemical enrichment, and cosmic energy budgets. From a human perspective, placing WR104 into the bigger picture is humbling. It reminds us that while we may focus on this single star as a potential doomsday object, the universe contains billions of similar systems, many of which are inaccessible and unobservable. WR104's relative proximity and dramatic spiral make it exceptional in terms of study, but it is a tiny fraction of the massive, dynamic stellar population shaping the cosmos. The processes we see in WR104, binary interactions, wind collisions, dust formation, and potential supernova or GRB events, are occurring in countless other systems across the galaxy and universe, continuously influencing the evolution of matter on a grand scale. In essence, WR104 is a microcosm of cosmic extremes. Its beauty, energy, and potential power provide an accessible example of stellar processes that are widespread yet largely invisible. Observing it helps us understand not just one star, but the behavior of massive stars throughout the Milky Way and beyond, offering insight into how galaxies evolve, how chemical elements are distributed, and how extreme cosmic events occur. By situating WR104 in this broader context, we gain perspective. The Pinwheel Star is both remarkably unique and yet part of a vast stellar ecosystem. Its spiral plume is a local example of universal processes, reminding us of the scale, frequency, and interplay of high-energy astrophysical phenomena that define the life cycles of the most massive stars in the cosmos. As we reach the conclusion of our journey through the mysteries of the Pinwheel Star, it's worth reflecting on what makes WR104 truly extraordinary. It is both a cosmic ticking clock and a breathtaking work of nature, a star that embodies the eternal balance between beauty and danger. On the one hand, we see a delicate spiral of dust, elegantly coiling outward like a cosmic pinwheel, each loop a visual record of the binary star's orbital dance. On the other, we know that deep within its core, immense forces are at play, forces capable of producing supernovae, possibly gamma-ray bursts, and energies that dwarf anything humanity can imagine. WR104 is a reminder of the duality inherent in the universe. Its spiral dust plume, glowing in infrared light, evokes awe and serenity, a perfect geometric pattern etched across thousands of astronomical units. Yet, the same system harbors one of the most extreme physical environments in our galaxy. The Wolf-Rayet star at its center is shedding its outer layers at tremendous speed, producing supersonic winds and high-energy radiation, and edging ever closer to a catastrophic end. Observing WR104 is a lesson in contrasts. Serenity and violence, creation and destruction, predictability and randomness all coexist in one remarkable system. The Pinwheel Star also reminds us of our place in the cosmos. It is 8,000 light-years away, yet its influence, beauty, and potential danger reach us through the images captured by our instruments and the stories we tell about it. WR104 illustrates the vastness of cosmic timescales. Its eventual explosion will unfold over hundreds of thousands of years, a span incomprehensible compared to a human lifetime. And yet, in the present moment, we can witness the interplay of forces shaping its spiral, gaining insights into stellar evolution, dust formation, and binary dynamics that apply to countless other stars across the universe. There is also a philosophical aspect to WR104's story. It encourages humility and wonder, teaching us that the universe is not static or predictable. Forces far beyond our control shape the cosmos, creating patterns of staggering beauty even as they harbor immense potential energy. The star's spiral is not just an astrophysical phenomenon, it is a visual metaphor for the balance of order and chaos, elegance and power, present throughout the cosmos. At the same time, WR104 is a scientific treasure. Its proximity, visibility, and unique characteristics allow astronomers to study processes that would otherwise remain theoretical. Every loop of dust, every measured wind speed, every rotation of the binary system provides data that refine our understanding of stellar evolution, the life cycle of massive stars, and the origins of gamma-ray bursts. In essence, WR104 is both a laboratory and a spectacle, a star that educates and inspires simultaneously. Yet, for all its potential energy, WR104 poses no immediate threat to Earth. Its distance, the directionality of any possible gamma-ray burst, and the timescales involved make catastrophic consequences exceedingly unlikely. This knowledge allows us to appreciate the star's drama without fear, to marvel at its spiral while understanding that it exists safely on a cosmic stage far removed from our daily lives. In closing, the Pinwheel Star embodies a cosmic paradox. It is both ephemeral and enduring, ephemeral in the sense that its Wolf-Rayet stage is fleeting in cosmic terms, enduring in the sense that its spiral pattern will continue to evolve for thousands of years, shaping and enriching its surroundings. It is both dangerous and beautiful, a reminder that the universe operates on principles of both creativity and destruction, often intertwined in ways that challenge our perception and imagination. WR104 is more than a star, it is a symbol of the universe's grandeur. Its spiral is a dance of matter and energy, its winds a testament to stellar power, and its potential explosion a distant echo of the forces that drive cosmic evolution. Observing the Pinwheel Star allows us to connect with these universal processes, to witness a system at once delicate and extreme, and to appreciate the intricate, ongoing balance that defines the cosmos. So, the next time you think of the Pinwheel Star, remember this: it is a cosmic ticking clock, steadily advancing toward its dramatic fate, and simultaneously a breathtaking work of nature, spinning a spiral of elegance and precision across the galaxy. It is a testament to the awe-inspiring duality of the universe, where beauty and danger coexist, and where every orbit, every particle of dust, and every photon of light tells the story of life, death, and creation on a scale far beyond our own. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.